You know that smell, the one that hits you when the tide goes out on a warm afternoon, sharp, alive, faintly sulfurous, unmistakably of the sea. That is not salt, that is not seaweed, that is a molecule called dimethyl sulfide, exhaled by billions upon billions of microscopic ocean organisms. And on Earth, nothing else makes it. In April of 2025, the James Webb Space Telescope detected it in the atmosphere of a planet 124 light-years away. Not at trace levels. Not at the concentrations you would find standing on a beach at low tide. At concentrations 10,000 times higher than anything in Earth's oceans. A world drenched in the chemical signature of life. A world that, by every measure we have, should not smell this alive. And a signal that two completely independent instruments, looking through two completely separate windows of the spectrum, both refuse to let go of. Nobody knows what is producing it. That changed in the spring of 2025, when months of attempts to disprove the signal ran out of explanations, and the data was released to the world. Tonight, we go inside the most contested scientific discovery of our time, the planet K218b, the molecule, and the question that has divided the scientific community down the middle. We will trace the science behind the detection, examine the case for biology and the case against it, and sit with what either answer means for everything. If you find these journeys worth taking, liking and subscribing helps us keep making them. Now, 124 light-years away, something is exhaling. Let us find out what. There is a laboratory at the University of Cambridge where a scientist spent several months in the winter of 2024 trying to make a signal disappear. He was not trying to prove anything. He was trying to destroy something. He and his team had received data from the most powerful space telescope ever built. And what that data appeared to show was so significant, so far beyond anything the field had previously encountered, that the only responsible thing to do was to assume it was wrong and work backwards from there. They tested every calibration assumption. They modeled every alternative molecule. They ran the numbers again and again under different conditions, different frameworks, different statistical approaches. They were looking for the mistake. They were certain the mistake was there. It was not there. Niku Madhusudan had been building toward this moment for years, not consciously, not with any certainty that it would come, but through the slow accumulation of theoretical work that had positioned him, almost accidentally, at the exact intersection of the right question and the right instrument. When the second round of data finally finished processing in April of 2025, when the MIRI instrument aboard the James Webb Space Telescope returned its verdict, Madhusudan described the experience with a precision that told you everything about the weight of what he was feeling. He called it a shock to the system. He said it takes a while to recover from the enormity of it. Those words, from that man, in that context. Madhusudan is not a person given to drama. He is a person given to data. He is the kind of scientist who qualifies his qualifications, who uses the word potential where others might use the word proof, who writes papers in language so careful it can feel surgical. When a scientist of that disposition says a shock to the system, you understand that something unusual has happened to him, something the data did to him that data does not normally do. The signal his team could not eliminate is a molecule called dimethyl sulfide. You have already met it. It is the living smell of the ocean, the sharp, faintly sulfurous scent that fills your lungs when you stand on a beach at low tide and the algae is baking in the afternoon sun. On Earth, dimethyl sulfide is produced by marine phytoplankton, by billions upon billions of microscopic organisms that release it as a byproduct of their metabolic lives. It rises from kelp forests and plankton blooms and the churning surface layers of every ocean on the planet. And on Earth, in Earth's atmosphere, nothing else makes it. Not volcanoes, not lightning, not chemistry acting alone on rock or water or air. Dimethyl sulfide in Earth's atmosphere means life. It is as close to a biological signature as our planet produces. The James Webb Space Telescope detected it in the atmosphere of a planet 124 light-years away. Not at the concentrations you would find at a beach, not at trace levels requiring heroic statistical effort to extract from the noise. At concentrations roughly 10,000 times higher than anything found in Earth's oceans. A planet so saturated with this molecule that the combined chemical output of every ocean on Earth, multiplied and amplified, does not begin to describe it. 2 independent instruments detected it. Looking through 2 completely separate windows of the electromagnetic spectrum, with 0 overlap between their wavelength ranges, both returned the same answer. The near-infrared instruments in 2023, the mid-infrared instrument in 2025. Different detectors, different wavelengths, different observing campaigns separated by 2 years. The same signal. That is where we are. That is the ground we are standing on. And before we go any further, there is something you need to understand about what this is and what it is not. Because the gap between those 2 things is the central discipline this entire video will ask of you. The signal is real. The data exists. 2 instruments on the most sophisticated scientific observatory humanity has ever constructed have both returned it. But science does not declare a discovery because an instrument returns a signal. Science declares a discovery when that signal has been verified, subjected to every credible alternative explanation available, and survived. The current statistical confidence level for the dimethyl sulfide detection sits at 3 sigma. 3 sigma means the probability that the signal is a random fluctuation, a noise artifact, a statistical accident, is roughly 3 in 1,000. In most scientific fields, 3 sigma is considered excellent evidence. You could publish on 3 sigma in medicine or ecology or materials science and face no serious challenge to your rigor. But this is not medicine or ecology. This is a claim about life on another world. And for claims of that magnitude, the threshold is 5 sigma. 5 sigma means the probability of the signal being chance falls below 1 in 3.5 million. That is the bar used to confirm the Higgs boson. It is the bar used to confirm gravitational waves. It is the bar that any detection of life beyond Earth will need to clear before the scientific community accepts it as a fact. 3 sigma is not 5 sigma. The gap between them is not a bureaucratic formality. It is the difference between a compelling hint and an established fact. And right now, we are on the compelling hint side of that line. Hold that. Because the question of how we got here, of how humanity built an instrument capable of detecting a specific molecule in the atmosphere of a world more than a century of light travel away, is a story that begins not with the telescope, but with a trick that light plays when it passes through air. Every atom, every molecule in the universe absorbs light at specific wavelengths. Not all wavelengths, specific ones, determined by the quantum mechanics of how electrons behave in that particular arrangement of nuclei. Oxygen absorbs at certain frequencies. Water absorbs at others. Carbon dioxide has its own pattern. Dimethyl sulfide has its own. Each one is unique, a chemical fingerprint encoded in the spectrum of any light that passes through a gas containing that molecule. This is not a metaphor. It is a physical fact that has been known and exploited by chemists and physicists for well over a century. When you spread white light into its component wavelengths using a prism, you get a rainbow. But if that light has passed through a gas before reaching you, the rainbow has dark lines in it, specific frequencies missing, absorbed by the molecules the light moved through on its way to your detector. Read those lines, identify which frequencies are absent, and by how much, and you can tell exactly what chemistry that light has encountered. This technique is called spectroscopy, and in the context of studying planets around other stars, the specific version of it is called transmission spectroscopy. Here is how it works. K2-18b, the planet at the center of this story, orbits its star once every 33 days. During each orbit, there is a window of several hours when the planet passes directly between its star and us. From our perspective, the planet crosses the face of the star. This is called a transit. During a transit, most of the starlight that reaches us is simply blocked by the planet's solid bulk. But at the very edges, at the thin ring where the planet's atmosphere meets the vacuum of space, some of that starlight passes through. It enters the atmosphere on one side, travels through hundreds of kilometers of alien air, and exits on the other. And while it moves through that atmosphere, every molecule it encounters leaves its mark on it. Carbon dioxide absorbs certain wavelengths. Methane absorbs others. Dimethyl sulfide absorbs its own specific set. The light that reaches our telescope carries all of those absences encoded within it. Collect that light, spread it into its component wavelengths, look at which frequencies are diminished and by how much, and you can read the chemistry of an atmosphere you will never visit, around a planet you will never reach, orbiting a star your spacecraft could not arrive at within any human lifetime. Think about what that means. The light we collect from K218b left that star 124 years ago. It has been traveling through the darkness of interstellar space since before the First World War, and buried inside that ancient light is a chemical diary of everything that world's atmosphere has been doing, a record of which molecules were present, in what concentrations, at the thin ring of air where day becomes space. This would be extraordinary with any instrument. With the James Webb Space Telescope, it becomes something else entirely. The signals involved are almost incomprehensibly faint. When K218b transits its star, the total dimming of the starlight amounts to roughly 1%, the planet blocking that fraction of the stellar disk. The additional dimming caused by specific molecules absorbing light in the atmosphere is a fraction of that. A fraction of a fraction, spread across narrow wavelength ranges, embedded in photon noise and instrument noise, and the general difficulty of measuring something extraordinarily faint from an extraordinarily large distance. To extract that signal reliably, you need three things. You need a mirror large enough to gather an enormous number of photons, because statistical confidence in spectroscopy is built on photon count. And the more photons you collect, the more precisely you can measure which wavelengths are missing. You need instruments sensitive enough to distinguish between wavelengths separated by fractions of a micrometer. And you need a platform stable enough that the ordinary vibrations of mechanical systems or the thermal expansion of materials do not produce noise that swamps the signal you are trying to find. The James Webb Space Telescope was built to meet all three of these requirements at a level no previous instrument had approached. Its primary mirror stretches 6.5 meters across, composed of 18 hexagonal segments coated in a thin layer of gold. Gold, because it reflects infrared light more efficiently than any other practical material, and because the universe at the distances and temperatures this telescope was designed to study radiates primarily in the infrared. Those 18 segments, each roughly the size of a large dining table, unfurled in the 2 weeks following launch like the petals of some enormous mechanical flower, aligning themselves to within fractions of a wavelength of light, using actuators capable of adjustments measured in nanometers. The telescope orbits at the second Lagrange point, a gravitational equilibrium located approximately 1 million miles from Earth in the direction away from the Sun. At this position, the combined gravitational influence of the Earth and Sun keeps the telescope in a stable orbit while allowing it to remain in permanent alignment with Earth's shadow. A sunshield, the size of a tennis court, made of 5 layers of a material called Kapton, keeps the telescope perpetually shaded, because the instruments aboard need to operate within a few degrees of absolute zero. At those temperatures, the telescope's own thermal radiation becomes negligible, and the faint infrared signals from distant worlds can be measured without the instrument drowning them in its own warmth. 2 separate instrument packages were turned toward K218b. The first, the near-infrared spectrographs observing in 2023, covered wavelengths from roughly 0.8 to 5 micrometers. That observation returned detections of carbon dioxide and methane, and the first indication of dimethyl sulfide. The second, the mid-infrared instrument known as MIRI, observing in 2025, covered 6 to 12 micrometers, a completely separate wavelength range, zero overlap with the first observation, a completely different set of molecular absorption features accessed through a completely different detector, and the dimethyl sulfide signal appeared again. Here is what that independence means. If the first detection had been a calibration artifact, a ghost produced by some quirk specific to the near-infrared instruments, it would not appear in the mid-infrared data. If it were an error in one analysis pipeline, it would not survive a completely independent observing campaign using different hardware 2 years later. The two detections share no common instrument, no common wavelength range, no common data processing assumptions. They are genuinely independent lines of evidence pointing at the same molecule in the same atmosphere. That is not proof, but it is the architecture of evidence that serious claims are built from. There is one more detail about this detection that sits quietly at the edge of everything else, and it is the kind of detail that changes the weight of the conversation entirely. In 2021, 4 years before the Miri observation confirmed the signal, Madhusudan published a theoretical paper. It described a class of planet, worlds with thick hydrogen atmospheres and global liquid water oceans, and it argued that if life existed in those oceans, specific molecules produced by that biology would accumulate in the hydrogen atmosphere to concentrations far higher than anything found on Earth. The paper named the molecules. Dimethyl sulfide was among them, and it specified that those concentrations would be within reach of the James Webb Space Telescope. The theory came before the observation. The prediction existed before the instrument was turned toward the target. That sequence matters more than almost anything else in this story, and we will return to it. But to understand why the theory predicted what it predicted, and why the planet it described is unlike anything in our solar system, we need to go to K218b itself, to understand what it actually is, how it got here, and why it has become the most scrutinized world in the history of astronomy. K218b is 8.5 times the mass of Earth. It is 2.5 times Earth's radius. It sits 124 light-years away in the direction of the constellation Leo, completing one full orbit around its star every 33 days, at a distance of roughly 13 million miles. That last number, 13 million miles, sounds close until you consider that Mercury, the innermost planet in our solar system, orbits the Sun at 36 million miles. K218b is nearly 3 times closer to its star than Mercury is to ours, and yet it sits comfortably within what astronomers call the habitable zone. That fact alone tells you something important about the star it orbits, and we will get to that star. But first, the planet itself, because K218b belongs to a category of worlds so common in the galaxy and so completely absent from our own solar system that we had almost no framework for thinking about it until the last 15 years. It is called a sub-Neptune. Too large to be a rocky planet, too small to be a gas giant. A world that sits in the size range between the two, with a density that falls somewhere in the middle, and, as it turns out, with properties that make it one of the most scientifically significant objects we have ever identified. Here is the thing about sub-Neptunes. When the Kepler Space Telescope surveyed the sky between 2009 and 2018, cataloguing the sizes and orbital periods of thousands of planets around other stars for the first time, one result came back more clearly than almost any other. The most common type of planet in our galaxy is not a rocky world like Earth. It is not a gas giant like Jupiter. It is something in between, a world between 1.5 and 4 times Earth's radius, in vast numbers, orbiting stars all across the Milky Way. Astronomers had spent decades assuming our solar system was a reasonable template for what planetary systems look like. Kepler told us, with unmistakable clarity, that we were wrong. A researcher named Benjamin Fulton, working with the California Kepler survey, went further. When he and his colleagues plotted the distribution of known planet sizes carefully, they found something unexpected within the sub-Neptune population: a gap, a near desert in the distribution of planet radii, centered around 1.5 to 2 Earth radii, separating two distinct groups. On one side, smaller rocky worlds. On the other, larger planets with substantial gaseous envelopes. The gap itself is caused by a process called photoevaporation, intense stellar radiation stripping the lighter atmospheric layers from certain planets over billions of years, leaving behind a bare, rocky core. The planets that survive with their atmospheres intact, the ones large enough or well shielded enough to hold on, become sub-Neptunes, and K218b, at 2.5 Earth radii, sits squarely in that surviving population. This matters for a specific reason. Sub-Neptunes are the most abundant planet type in the galaxy. They are almost certainly orbiting a significant fraction of the hundreds of billions of stars in the Milky Way. And yet, because our solar system contains none, we know almost nothing about what they are actually like inside. We have no nearby example to send a probe to. We have no close analog to study in detail. K2-18b, because it transits a relatively small and nearby star, frequently enough to make atmospheric characterization possible, has become our best current window into what this dominant class of world is actually made of. The planet was first detected in 2015 by the K2 mission, a repurposed version of the original Kepler telescope, operating after 2 of its reaction wheels failed. The mission found K2-18b the same way all transit photometry works, by watching the brightness of the host star dip slightly and repeatedly as the planet passed in front of it. The dip was small but consistent. The planet was real. Understanding what it was made of took years and a better instrument. In 2019, a team led by Björn Benneker at the Université de Montréal used the Hubble Space Telescope to observe K2-18b during multiple transits. What they found was the first tentative detection of water vapor in its atmosphere. Not confirmed, not definitive, but there. A hint in the near-infrared spectrum that this world had something wet in its envelope. That result, cautious as it was, elevated K2-18b on the priority list for the telescope that was then still being tested and prepared, the James Webb Space Telescope. K2-18b had everything you want in a target if you are trying to read an exoplanet atmosphere. A star small enough that the planet's transit produces a measurable dimming. A transit that repeats every 33 days, giving you multiple observation windows each year. An atmospheric envelope thick enough to produce detectable spectral signals. And a location in the habitable zone, that band of orbital distance where temperatures could, in principle, permit liquid water. When JWST began science operations, K2-18b was near the top of the queue. Its year of 33 days is worth sitting with. A complete orbit in just over 4 weeks. The planet swings around its star and returns to the same position in the time it takes most people to move through a single month. And because its orbit is slightly elliptical, bringing it closer to the star at one point and carrying it farther at another, the energy raining down on the planet changes by roughly 43% between those two extremes. Every 33 days, a cycle of warming and cooling, of higher flux and lower flux, repeating without pause. Whatever lives on this world, if anything does, lives in that rhythm. In 2021, Madhusudan published a paper that proposed a name for what K2-18b might be. The name was Halcyon, a word built from the 2 things the model requires: hydrogen and ocean. A Halcyon world, as the paper defined it, is a sub-Neptune with a thick hydrogen-helium atmosphere and a global liquid water ocean beneath it. No continents, no land of any kind, just water covering the entire surface from one side to the other, as far down as the interior physics allows. The paper did not invent this possibility from nothing. Water-rich sub-Neptunes had been discussed in planetary science before. What Madhusudan's team did was examine the idea systematically for the first time, asking not just whether such worlds could exist, but whether they could be habitable, and if so, what the signatures of that habitability would look like to a telescope. The answers were striking. Picture the interior of K2-18b in the Halcyon model. At the center, a rocky core, compressed under pressures so extreme that the rock itself behaves in ways no Earth laboratory can replicate. Iron and silicate minerals locked into exotic crystalline structures by the weight of everything above. Surrounding that core, a layer of what planetary scientists call high-pressure ice, not the frozen water you know from a glass or a freezer, but water molecules forced into dense, crystalline states by pressures millions of times greater than anything at Earth's surface. The word ice is almost misleading. It is water under conditions so extreme it has become something else entirely. Above that, in the Hessian model, liquid water. A global ocean with no shore, extending across the entire planet. And above the ocean, pressing down on it with a weight Earth's atmosphere cannot approach, a thick blanket of hydrogen and helium stretching hundreds of kilometers into space. The pressure at the ocean's surface, where atmosphere meets water, may be roughly 100 times greater than sea level pressure on Earth. Under that weight, water does not behave like the water in your kitchen. Its boiling point rises dramatically. At 100 times atmospheric pressure, water remains liquid at temperatures well above 100 degrees Celsius. At higher pressures still, it can enter what is called a supercritical state, where the boundary between liquid and gas dissolves entirely, and you have a dense, flowing fluid with properties of both. Whether the surface layer of K218b's ocean is liquid water, supercritical fluid, or something between the two depends on temperature. And temperature depends critically on cloud cover, which turns out to be one of the hardest things to model in planetary science. More on that later. Here is what matters for the biology. Hydrogen is not oxygen. The air of Earth is 21% oxygen, and almost every complex organism on this planet depends on it. The assumption runs so deep in our intuitions that it can feel like a fundamental requirement for life rather than a local condition of one particular world. It is not a fundamental requirement, it is what Earth happened to end up with. Earth's atmosphere did not always contain free oxygen. For more than 2 billion years, longer than animals have existed, longer than complex cells have existed, the biosphere operated without it. Life did not wait for oxygen. Life eventually produced it, as a byproduct of photosynthesis, transforming the planet's chemistry from the outside in. The organisms that accomplished this were single-celled and metabolically ancient, and their descendants still exist today in the oxygen-free zones of the deep ocean, in volcanic sediments, in the subsurface rock kilometers below our feet. Among the most relevant of these, for K218b, are the methanogens, a group of organisms belonging to the archaea, one of the three great domains of life on Earth. Methanogens do not breathe oxygen. They consume hydrogen gas and carbon dioxide, combining them in a metabolic reaction that releases energy and generates methane and water as waste. They have been doing this for billions of years. They live in swamps and rice paddies and the digestive systems of every large animal. Some have been found kilometers underground. They are among the most ancient and durable life forms we know. K218b's atmosphere, as detected by the James Webb Space Telescope, contains hydrogen. It contains carbon dioxide. It contains methane. These are precisely the compounds methanogens consume, and precisely the products they release. That is not proof, but it is the kind of coherence that separates a reasonable biological hypothesis from a desperate one. Now consider dimethyl sulfide in this framework. On Earth, it is produced as an incidental byproduct of a metabolic process in marine phytoplankton, a compound called dimethyl sulfoniopropanate, which organisms use as an osmotic regulator, breaks down and releases dimethyl sulfide as a secondary product. The sulfide was never the point, and in Earth's oxygen-rich atmosphere, ultraviolet radiation destroys it within days. The ocean keeps producing it. The atmosphere keeps dismantling it. The result is a background level that is measurable but low. In a hydrogen atmosphere, that chemistry changes. The dominant reactions that break down dimethyl sulfide in Earth's air involve oxidants, molecules that react with it and consume it rapidly. A hydrogen-rich atmosphere has far fewer oxidants. The molecule, once produced, survives far longer, 10 times longer perhaps 100 times longer in certain conditions, which means that even a comparatively modest biological source, far less productive per unit area than Earth's oceans, could drive atmospheric concentrations far higher than anything our planet achieves. Madhusudan's 2021 paper worked through these numbers. It specified that a Hycean world with active marine biology would accumulate dimethyl sulfide in its hydrogen atmosphere to concentrations detectable by the James Webb Space Telescope. It named the instrument that did not yet exist at that time, performing science it had not yet begun, and it said, "If life is present on this kind of world, this is the signal it will leave." 4 years later, that instrument found the signal. You can question the interpretation. You can, and scientists actively do, contest the statistical methods, dispute the atmospheric models, and propose alternatives that require no biology at all. All of that is part of this story, and none of it is going away. But the sequence itself is not in dispute. The prediction came first. The observation came second. In science, that order of events carries a weight that is difficult to manufacture after the fact and impossible to dismiss. A theory that specifies what you will find before you look is a theory doing something real. The planet is still out there, completing its 33-day orbit, indifferent to the argument it has started. And the question at the heart of that argument, is this a living world or a dead one dressed in the chemistry of life, is what the rest of this story is about. The star that K2-18b orbits is called K2-18. That name is not poetic. It is a catalogue designation, inherited from the mission that first identified the system. But the object behind that designation is worth understanding in some detail, because the character of the star shapes everything about the planet. What its surface might look like, whether its atmosphere could survive, whether any chemistry in that atmosphere is being continuously created or continuously destroyed, and why, despite all the ways this star is trying to make the planet hostile, K2-18b is one of the most observable worlds we have. K2-18 is a red dwarf. Specifically, it is classified as an M2.5 dwarf, a type of star with roughly a third of the Sun's mass and about 1/40th of its luminosity. It burns dimmer and cooler than our Sun, emitting most of its light in the red and near-infrared, rather than in the yellow-white visible spectrum that illuminates our days. At roughly 2.5 billion years old, it is considered a middle-aged example of its class. Not young and furiously active, not ancient and quiet, somewhere in between. Here is why that matters. Red dwarfs are the most common stars in the Milky Way. Estimates place them at roughly 70 to 75% of all stars in the galaxy, meaning that if you picked a star at random from the 400 billion or so in the Milky Way, your chances of landing on a red dwarf are better than 2 to 1. They are everywhere, and because they burn their hydrogen so slowly and so carefully, they last for extraordinary lengths of time. A red dwarf of modest mass could continue fusing hydrogen for 10 trillion years. Our Sun, by comparison, has a total lifespan of roughly 10 billion years and is already approaching its middle age. A red dwarf at the same age would be barely out of infancy. That longevity sounds like a gift for any planet in its orbit. 10 trillion years is an almost incomprehensible span of time for life to develop, diversify, and potentially become something we would recognize. But the gift comes with a condition attached. Red dwarfs, particularly in their younger and more active phases, are extraordinarily violent. Stellar flares, eruptions of magnetic energy from the surface of a star, releasing bursts of X-ray and ultraviolet radiation, along with streams of charged particles, occur on the Sun with some regularity. The largest solar flares are genuinely powerful events, capable of disrupting radio communications and satellite operations on Earth. But Earth is 93 million miles from the Sun and protected by a robust magnetic field. A red dwarf flare of comparable or greater energy, directed at a planet orbiting 13 million miles away, with no guarantee of equivalent magnetic protection, is a different proposition entirely. On younger, more active red dwarfs, such flares can occur multiple times daily, each one a pulse of radiation intense enough to accelerate the stripping of an atmosphere or to drive photochemical reactions in the upper air that destroy complex molecules. K2-18 is relatively calm for its type, but relatively calm means it still flares. It still bombards K218b with radiation that our Sun does not deliver to Earth in comparable doses. The question of what that bombardment does to any chemistry and any potential biology in the planet's atmosphere is one of the central uncertainties in this entire investigation. There is another consequence of orbiting so close to a star for so long, and it shapes the physical reality of K218b more profoundly than anything else in its environment. It is called tidal locking. You already know this mechanism. The Moon always shows the same face to Earth. That is not a coincidence or an accident. It is the result of billions of years of gravitational interaction between the Earth and Moon, in which the tidal forces generated by Earth's gravity gradually slowed the Moon's rotation until it matched the time the Moon takes to complete one orbit. The Moon's day and the Moon's year became the same length. One side permanently faces us, the other permanently faces away. The same process operates on any body orbiting close to a massive object for a sufficiently long time. And K218b, at 13 million miles from its star, orbiting every 33 days for over 2 billion years, is almost certainly tidally locked to K218 in exactly this way. Picture what that means for the planet. One hemisphere faces the star permanently, the same face, receiving the same light, every hour of every day for billions of years. The star does not rise, it does not set. It hangs in the sky above one side of the planet, motionless, pouring energy down onto the surface at a constant and unrelenting rate. Temperatures on this day side could be high enough to prevent liquid water from persisting at the surface, to break apart complex molecules in the upper atmosphere, and to drive violent convection in the air as heated gas expands and rises. The opposite hemisphere has never seen the star. Not once, in billions of years, has a single photon from K218 reached the night side directly. Temperatures there plunge. The air cools, contracts, and sinks. In the darkest, most sheltered regions of the permanent night side, temperatures may drop to 60 degrees below zero or colder, a landscape of perpetual darkness, frozen and still. Between these two extremes runs the terminator, the boundary where day becomes night, a ring that circles the entire planet at the line where the star sits permanently on the horizon. Here, temperatures are most moderate. Here, the hot expanding air of the day side meets the cold contracting air of the night side and is driven around the planet in an endless atmospheric circulation, a global wind driven not by the turning of a world on its axis, but by the permanent temperature difference between a hemisphere that has always faced a star and a hemisphere that never has. Wind speeds in this region could reach hundreds of miles per hour, a constant roar of hydrogen moving from the baking day side toward the frozen night. If any life exists on K218b, the terminator is where conditions would be most survivable. The narrow band of perpetual dusk, where neither extreme dominates, where the atmosphere churns with energy, and where any ocean, if it exists, would circulate heat from one side of the planet to the other. The most important real estate on the world, and we cannot directly observe it. Here is the paradox that defines red dwarf research, and it is a real paradox worth holding. These stars are simultaneously the most dangerous hosts for biology and the most scientifically productive targets for biosignature searches. The habitable zones of red dwarfs are so close to the star that planets transit their host stars frequently and visibly. A planet in the habitable zone of a sun-like star might transit once a year and spend only a few hours crossing the stellar disk. A planet in the habitable zone of a red dwarf might transit every few weeks, and the transit is relatively easy to detect because the planet is large compared to the small star. The very nearness that makes the radiation environment so punishing also makes the atmospheric signal accessible to instruments like the James Webb Space Telescope. Red dwarf planets are, in the language of detection, observable. K218b is the most observable of all of them within its class. That K218b still has an atmosphere at all, after more than 2 billion years of exposure to the radiation environment just described, is itself a fact that requires explanation. Mars lost most of its atmosphere roughly 3 to 4 billion years ago. The process was slow but inexorable. The solar wind, a continuous stream of charged particles flowing outward from the Sun, gradually stripped the Martian atmosphere molecule by molecule as the planet's magnetic field weakened and could no longer deflect the incoming particles. The result, over geological time, was a world stripped nearly bare, surface pressure less than 1% of Earth's, unable to support liquid water, unable to shield the surface from ultraviolet radiation. A planet that may once have been hospitable, becoming one of the most hostile surfaces in the solar system. K218b has faced a more intense version of that same stripping process, from a star more active than the Sun, at a distance 3 times closer than Mercury for billions of years, and yet the atmosphere is there, thick, massive, detectable from 124 light-years away, with enough richness of chemical content to keep some of the best scientists in the world arguing about what it contains. Why? 3 explanations compete, and they are not mutually exclusive. The first is that the planet has a strong internal magnetic field, generated by convection in its large, hot interior, that deflects the charged particles of the stellar wind before they can interact with the upper atmosphere and drive escape. Earth's magnetic field protects our atmosphere in exactly this way. A planet 8.5 times Earth's mass, with a correspondingly larger and more energetic interior, might generate a proportionally more robust magnetic shield. The second explanation is simpler and more brutal. The atmosphere is just enormous. At K218b's mass and composition, the total inventory of hydrogen in the envelope is so vast that even significant losses over billions of years represent only a small fraction of the total. You can strip away a great deal and still have a great deal left. The atmosphere survives not because it is defended, but because it is inexhaustible on the timescales involved. The third possibility is replenishment, that volcanic and geological activity in the planet's interior continuously releases fresh hydrogen and other gases into the atmosphere, replacing what is lost to space approximately as fast as the star removes it. A planet that breathes, in a sense. One that maintains its envelope, not by holding it still, but by continuously producing more. Any of these could be the answer. Most likely, some combination of all 3. What matters for the question of life is the implication. A world that has maintained a stable, massive atmosphere for over 2 billion years in this environment has not merely survived. It has persisted with the kind of long-term stability that life on Earth required to get started and develop any complexity. Earth's earliest life emerged within roughly 500 million years of the planet's formation. K218b has had more than 2 billion years of atmospheric stability. If conditions were otherwise right, that is an enormous span of time. The radiation environment also reaches directly into the chemistry of the dimethyl sulfide signal, and this is where the atmosphere's survival story intersects with the detection story in a specific and important way. Ultraviolet radiation, when it reaches the lower layers of a planetary atmosphere, can break apart complex organic molecules. On Earth, ultraviolet photolysis destroys dimethyl sulfide in the atmosphere within days. The ocean surface produces it continuously, the upper atmosphere dismantles it continuously, and equilibrium is maintained at concentrations that are measurable but low. In K218b's hydrogen envelope, the same UV-driven destruction occurs, but more slowly. The overlying gas partially shields the lower atmosphere from the worst of the ultraviolet flux. The molecule, once released into the air above whatever surface the planet has, survives longer before it is broken apart. It accumulates. The longer survival time is part of why the 2021 theoretical work predicted that biological dimethyl sulfide production on a Hycean world would reach concentrations far exceeding anything on Earth. But the radiation environment also creates a constraint. Whatever organisms might be generating dimethyl sulfide on K218b, if biology is the source, they are doing so against a background of continuous destruction from above. The star periodically flares. Ultraviolet pulses reach deeper into the atmosphere during the most energetic events. The molecule's survival time is not constant. It varies with the star's activity level, with the orbital position of the planet, with the height at which the molecule is released. The biology, if it is there, is producing against that variable destruction rate. It is not enough for life to exist. It has to be producing abundantly enough, consistently enough, to maintain the observed concentration through the full cycle of what this star throws at it. That is a demanding requirement. It is not an impossible one. Life on Earth routinely satisfies demanding requirements. There is an organism called Deinococcus radiodurans, a bacterium found in environments where radiation doses would kill almost anything else, that can survive exposure to radiation 10,000 times greater than what kills a human being. It has been found in the cooling water of nuclear reactors, in Antarctic permafrost, in samples returned from the upper stratosphere, not thriving in those environments exactly, but viable, intact, its DNA shredded by radiation and reassembled repeatedly by repair mechanisms so efficient they represent something close to a biological answer to the worst conditions a star can generate. Life, when it finds a foothold, does not give it up easily. There is one more dimension to the atmosphere's survival that deserves attention, because it connects to something larger than just K2-18b. A biosphere, a planet-wide system of organisms metabolizing and producing gases, is not passive with respect to its own atmosphere. On Earth, life transformed the atmosphere. The oxygen that makes our air breathable did not exist in quantity before photosynthetic organisms put it there. Life has been actively modifying Earth's atmospheric chemistry for billions of years, and in doing so, it has stabilized conditions that favor its own continuation. A hydrogen atmosphere is not exempt from this principle. If biology were present on K2-18b, it would be participating in the chemistry of the envelope, consuming some molecules, producing others, potentially maintaining conditions that favor its own persistence. The atmosphere that has survived for 2 billion years may not merely be evidence that the planet is geologically stable. It may be evidence that something has been keeping it that way. That is a speculation. It is clearly labeled as such. But it is the kind of speculation that arises naturally from the data, and it illustrates why this particular detection, on this particular planet, around this particular star, feels different from what has come before. The signal is real. The planet is strange. The star is difficult. And none of those facts make the question any easier to answer. There is a number that sits at the center of the case against the Hessian model, and it is worth stating plainly before anything else. To maintain liquid water at the surface of K2-18b, the ocean that the Hessian hypothesis requires, the planet would need to reflect approximately 92% of all the light arriving from its star back into space. 92%, reflecting 19 out of every 20 photons before they can warm the surface. That number comes not from one group, but from two independent research teams working separately, arriving at the same result in 2025. To understand why that number is so significant, you need to understand what albedo is and what real planets achieve. Albedo is a measure of reflectivity, a value between 0 and 1, expressing what fraction of incoming light a surface sends back, rather than absorbing. A perfectly black surface has an albedo of 0. It absorbs everything. A perfect mirror has an albedo of 1. It reflects everything. Real planetary bodies fall between those extremes. Earth, averaging across oceans and land and ice and clouds, has an albedo of roughly 0.3. It reflects about 30% of incoming sunlight. Fresh snow reaches close to 0.9. Venus, perpetually covered in dense, bright clouds of sulfuric acid, achieves around 0.65, among the highest of any body in our solar system, and one of the reasons Venus is so extraordinarily bright in the night sky. 92% is higher than Venus, higher than fresh snow. It is essentially the albedo of a perfect mirror. No known planet achieves it. No known atmosphere produces it naturally. And the only physical mechanism that could plausibly generate such extreme reflectivity is an extraordinarily dense layer of highly reflective cloud, positioned at precisely the right altitude to intercept almost all incoming starlight before it reaches the surface below. The current JWST observations of K2-18b show no compelling evidence for such cloud layers. Neither the 2023 near-infrared data nor the 2025 mid-infrared data carries the spectral signatures that dense, high-altitude cloud coverage would be expected to produce. That absence does not prove the clouds are not there, but it is a constraint that the Heysian hypothesis must answer, and answering it requires either demonstrating that the albedo calculation is wrong or demonstrating that clouds at K2-18b could produce extreme reflectivity without leaving a detectable atmospheric fingerprint. This is where the analysis runs into one of the deepest difficulties in planetary science, which is the problem of cloud modeling. Clouds are the most poorly understood variable in any atmospheric model. This is not a minor technical limitation. It is a fundamental constraint on what we can confidently predict about planetary climates. We live on a world we can fly instruments through, launch weather balloons into, sample directly, and observe from thousands of ground stations simultaneously. And we still cannot fully reproduce the behavior of Earth's clouds in our best climate models. The feedbacks involved are complex and sensitive. Small changes in temperature, humidity, and aerosol content drive large changes in cloud formation and dissipation. The models capture the broad behavior but struggle with the details, and the details matter enormously for calculating how much sunlight a planet actually absorbs. Martin Turbot, working on the thermodynamics of water-world surface conditions, approached the K2-18b problem from the irradiation side. The combination of stellar flux, atmospheric pressure from the massive hydrogen envelope, and the greenhouse warming produced by that envelope may be enough to push surface temperatures above the stability threshold for liquid water, even without extreme reflectivity. Depending on where exactly the clouds form, how optically thick they are, and how efficiently they trap outgoing heat versus reflecting incoming light. The calculation is not clean, the uncertainty ranges are large, but the direction of the constraint is clear. Maintaining a liquid ocean at K2-18b's surface is harder than the Heysian model's most optimistic versions suggest, and the current data does not provide the cloud evidence that would make it easier. The critical epistemological point here is one that applies to much of what surrounds this detection. Absence of evidence is not evidence of absence. The fact that current JWST data does not reveal the dense cloud layers the albedo calculation requires does not prove those clouds are absent. It means we have not detected them. Those are different statements, and the difference matters. Cloud signatures in transmission spectroscopy are difficult to extract. Clouds that form at low altitudes or that are optically thin may leave weak or ambiguous spectral imprints. The data we have is not sufficient to rule them out. What additional observations could do is constrain the cloud structure more tightly. Thermal emission measurements, looking at the infrared radiation the planet itself radiates rather than transmitted starlight, could reveal information about the temperature structure of the atmosphere at different altitudes, and by extension, constrain where cloud layers form and how thick they are. Phase curve observations, tracking how the planet's brightness changes over the course of an orbit as different portions of its surface and atmosphere rotate into view, could map the temperature distribution across the planet and place limits on the efficiency of heat redistribution from the day side to the night side. Neither of these observations has yet been completed at sufficient depth to resolve the cloud question. The albedo problem is real. It is a genuine constraint on the Heysian model. It is not decisive, but it is the kind of constraint that demands a direct response, not a dismissal, and the Heysian hypothesis has not yet provided one that closes the question. Set the ocean aside for a moment. Set aside the question of whether liquid water can persist at K2-18b's surface at all, because there is a scientist at the University of Cambridge who would like you to consider a different picture entirely, one in which the question of liquid water is not uncertain, but simply wrong, and what lies beneath that hydrogen atmosphere is not an ocean of any kind. Oliver Shortall is a geochemist. where Madhusudan builds models of planetary atmospheres and asks what chemistry they would contain if life were present. Shortle builds models of planetary interiors and asks what chemistry they would produce on their own, without any biology at all. His starting point is not the atmosphere, it is the rock. At K218b's mass, 8.5 times Earth's, the pressure and temperature at the base of the hydrogen atmosphere, where it interfaces with whatever solid or liquid material lies beneath, are extreme by any measure. Extreme enough, in Shortle's models, to produce a planet whose surface is not water, but magma, a worldwide sea of molten rock, churning with convection currents that carry material up from the interior and drag it back down again over timescales of centuries or millennia, sitting directly beneath the hydrogen envelope and interacting with it continuously through a cascade of chemical reactions. This is not a fringe proposal. It is a class of planetary structure that serious modeling work supports for sub-Neptunes in this mass and density range, and the atmospheric chemistry it produces is, from the outside, uncomfortably similar to what the James Webb Space Telescope has observed. Here is how the magma ocean chemistry works. When a hot silicate melt sits at the base of a hydrogen atmosphere, it dissolves gases from that atmosphere into the liquid rock and releases others from the interior in continuous exchange. Nitrogen, which should be abundant in a planet of K218b's mass and bulk composition, gets dissolved into the melt efficiently. That explains why K218b's atmosphere appears to be missing ammonia, a nitrogen compound you would expect to detect in a world of this composition. The Hessian model accounts for the ammonia absence by invoking biological processes that consume it. The magma ocean model accounts for it by simple chemistry. The melt absorbs it. The melt also releases gases. Volcanic outgassing from a magma ocean produces methane and carbon dioxide, the same carbon-bearing molecules that JWST detected in K218b's atmosphere, and that the 2023 paper flagged as significant, not because a biological process generated them, but because hot rock reacts with the gases above it in ways that produce organic compounds without any organism involved. Carbon chemistry at high temperatures and pressures has been doing this since before the first living cell existed anywhere in the universe. And then there is the sulfur. At the temperatures prevailing in a magma ocean, hydrogen sulfide, a volcanic gas released from the interior, reacts with the carbon chemistry of the overlying atmosphere in ways that can produce organosulfur compounds, including, in laboratory conditions, dimethyl sulfide. The reaction pathways exist. The chemistry is real. The question is not whether abiotic dimethyl sulfide production can occur at a magma-atmosphere interface, but whether it can occur at the rates required to explain the concentration K2-18b apparently shows. This is where the yield gap appears, and it is the most honest place to locate the current state of the argument. When chemists measure the abiotic production of dimethyl sulfide through thermal sulfur chemistry under Earth laboratory conditions, the yields are low, roughly 10 to 100 times lower than would be needed to explain the observed atmospheric concentration. If those yields are representative, the magma ocean model cannot produce enough dimethyl sulfide to account for what JWST is detecting. The abiotic pathway exists, but is too weak, except that those laboratory measurements were made under Earth laboratory conditions, room temperature, atmospheric pressure, controlled chemical environments that share almost nothing with the extreme pressure and temperature of a sub-Neptune interior. How thermal sulfur chemistry behaves at tens of thousands of atmospheres of pressure and temperatures of thousands of degrees is not well characterized. The extrapolation from Earth laboratory results to a magma ocean environment is uncertain in both directions. The yields could be lower than expected, or they could be dramatically higher. Nobody knows, because nobody has measured it. Here is where the Rosetta mission enters the picture, and it enters carrying one of the most important pieces of evidence in the entire debate. Rosetta was an ESA spacecraft that spent 2 years orbiting Comet 67P/Churyumov-Gerasimenko, studying its chemical composition in extraordinary detail before landing on its surface in November of 2016. Among the instruments aboard was the Rosina mass spectrometer, a device capable of identifying individual molecules in the comet's thin, volatile halo. When researchers subsequently analyzed the Rosina dataset for sulfur-containing organic compounds, they found something that had not been widely discussed at the time of the original mission: dimethyl sulfide. In the chemistry of a comet, ancient material left over from the formation of the solar system, never touched by any living thing, carrying within it the same molecule that is being proposed as a biosignature at K2-18b. Comets are not biologically active. They have never been warm enough, wet enough, or chemically complex enough to support life. The dimethyl sulfide in Comet 67P formed through cold interstellar chemistry, through the interaction of simple molecules under ultraviolet irradiation in the frozen, lightless environment of the early solar nebula. It did not need a cell to produce it. It needed only time, ice, and radiation. This matters enormously. Every proposed biosignature has what scientists call an abiotic escape route, a non-biological process that can produce the same molecule. For many years, dimethyl sulfide was considered one of the more defensible biosignatures because its known abiotic production pathways on Earth were relatively limited. The Rosetta finding changed that. It demonstrated that dimethyl sulfide forms in space chemistry without any biology, under conditions far simpler and more primitive than a magma-ocean interface. The abiotic escape route for dimethyl sulfide is not hypothetical. It has been directly observed. The question this raises, the genuinely open question that neither side of the debate can currently resolve, is whether the concentrations seen at K2-18b can be explained by abiotic processes alone. 10,000 times the concentration of Earth's oceans is a large number. Abiotic production in cometary ice is a real phenomenon, but it occurs at rates and scales that are not obviously sufficient to explain an atmospheric concentration of that magnitude. The magma ocean model provides a plausible mechanism, but an uncharacterized yield. The biological model provides a coherent source, but an unproven biology. Both explanations are alive, neither is proven. And the data that would distinguish between them, direct measurement of the planet's thermal emission, higher resolution mid-infrared spectroscopy, detection or non-detection of additional molecules that would be present under one model and absent under the other, does not yet exist. Apply Occam's razor if you want to. The magma ocean model requires no new physics, no independent origin of life, no coincidental alignment of habitability conditions, no novel biochemistry in an exotic environment. It requires only that a sub-Neptune of K2-18b's mass and composition behave like a sub-Neptune of K2-18b's mass and composition. That is the simplest explanation consistent with the data, but simplicity is not truth. It is a tiebreaker, and only when the competing explanations are otherwise equal. The Hessian hypothesis carries the weight of its predictive success. The magma ocean model carries the weight of its geological plausibility. The data is insufficient to decide between them, and anyone telling you otherwise is telling you something the science does not yet support. The disagreement over what K2-18b's atmosphere contains is not only a disagreement about chemistry or geology, it is also, at a technical level, a disagreement about method, about how you extract molecular information from spectral data, what assumptions you are permitted to build into your analysis, and whether the answer you arrive at is a property of the planet or a property of the model you chose to run. This is the statistical battle, and it matters because it sits underneath everything else. When astronomers analyze transmission spectroscopy data from an exoplanet, they use a technique called atmospheric retrieval. The basic idea is to compare the observed spectrum, the pattern of wavelengths that are absorbed by the planet's atmosphere during a transit, against a library of model spectra generated by assuming different atmospheric compositions. You try different combinations of molecules in different concentrations, run each combination through a model that predicts what its transmission spectrum should look like, and find the combination that best fits what the telescope actually measured. The molecule or set of molecules that produces the closest match to the data is, in principle, what the atmosphere contains. The problem is that retrieval is not a neutral procedure. The models you run, the molecules you include, the assumptions you make about atmospheric structure, temperature, pressure gradients, and cloud properties, all of these choices shape the result. A retrieval that includes dimethyl sulfide in its library and a retrieval that does not will return different answers, even when applied to identical data. The science of atmospheric retrieval is rigorous and well developed, but it is not assumption-free. It cannot be. Madhusudan's team, in both the 2023 and 2025 analyses, used a targeted retrieval approach. They built detailed atmospheric models, incorporating the molecules they expected to find based on the theoretical framework they had developed, including dimethyl sulfide, and asked which combination of those molecules best fit the observed spectrum. Their models were multidimensional, accounting for the variation of temperature and composition with altitude, and they eventually expanded their molecular library to include 650 candidate species. In both observations, dimethyl sulfide emerged as the best fit among the sulfur-containing molecules considered. A researcher at the University of Oxford took a different approach. Jake Taylor's analysis of the MIRI data used what he called an unbiased retrieval, a method that makes no prior assumptions about which molecules to search for. Rather than building a model that includes dimethyl sulfide and asking how well it fits, Taylor's method feeds the spectrum into an algorithm that explores the full space of possible atmospheric compositions without weighting any particular molecule. The algorithm finds whatever combination of molecular features produces the best overall match to the data. What Taylor's analysis returned was not dimethyl sulfide. What it returned was something considerably more unsettling for the detection claim: results consistent with a flat spectral line, no statistically significant molecular features, an atmosphere that, according to this method, could not be clearly distinguished from one containing no absorbing species at all. A team working across institutions and drawing on colleagues associated with the University of Chicago compounded the difficulty. They took both datasets, the 2023 near-infrared observations and the 2025 MIRI data, and combined them in a single joint analysis, treating them together rather than separately. Their conclusion was similar. When the full available data was considered together, there was no statistically significant detection of dimethyl sulfide, nor of dimethyl disulfide, a related molecule with overlapping spectral features that had been proposed as an alternative identification. Madhusudan's team responded to both challenges. Taylor's retrieval, they argued, used an oversimplified one-dimensional model of the atmosphere, a structure that represents the planetary atmosphere as a single column with uniform properties at each altitude, when in reality, a tidally locked planet like K218b has a complex three-dimensional structure, with significant differences in temperature and composition between the day side, the night side, and the terminator. In a three-dimensional atmosphere with those contrasts, overlapping molecular features at JWST's spectral resolution can produce signals that a one-dimensional model misidentifies or misses entirely. The unbiased retrieval, Madhusudan's team argued, was unbiased in its molecular assumptions, but not in its atmospheric geometry, and the geometric simplification was the source of the discrepancy. The Chicago Joint Analysis drew a different objection: the relative weighting applied to the two datasets, how much statistical influence each observation was given in the combined fit, was not, Madhusudan's team argued, physically motivated. Different assumptions about the weighting produced different results, and the choice of equal weighting between two observations of different quality and wavelength range is not obviously correct. The critics pushed back. The detecting team's atmospheric model, they noted, had changed substantially between the original 2023 paper and the responses to the 2025 challenges. More molecules were added to the retrieval library. More parameters were introduced to describe the atmospheric structure. More degrees of freedom were available for the model to fit the data. When you give a model enough free parameters, it can fit almost any dataset, not because the model is capturing something real, but because the added flexibility allows it to accommodate noise as if it were signal. The critics were not accusing Madhusudan's team of dishonesty. They were identifying a methodological risk that any scientist should take seriously: overfitting, the quiet enemy of clean inference. There is another ambiguity woven through all of this that no amount of reanalysis can currently resolve. Dimethyl sulfide and dimethyl disulfide, a structurally related molecule that can also be produced by biological processes, have absorption features that overlap at the wavelengths covered by JWST's current K2-18b observations. At the spectral resolution the telescope achieves in this wavelength range, the two molecules cannot be cleanly separated. The detection is not, strictly speaking, a detection of dimethyl sulfide specifically. It is a detection of a spectral feature consistent with one or both of those molecules. Distinguishing between them requires observations at wavelengths beyond 12 micrometers, where their absorption features diverge sufficiently to be individually identified. That data does not exist. It has not been collected, and it cannot be extracted from any existing observation by any analytical method, however sophisticated. This is the wall the debate has run into. Not a disagreement about how to interpret the same data, exactly, but a disagreement about a question that the existing data is insufficient to answer, and that will remain unanswered until more photons from more transits at more wavelengths are collected and processed. Here is where the honesty of the situation requires something uncomfortable. Both teams are doing legitimate science. Taylor's unbiased retrieval represents a genuine methodological advance, a way of approaching spectral data that reduces the risk of finding what you are looking for because you included it in the model. Madhusudan's expanded retrieval represents genuine expertise in atmospheric modeling, applied with care and rigor to a deeply complex dataset. The University of Chicago joint analysis represents a reasonable attempt to use all available evidence simultaneously. These are not bad scientists arguing in bad faith. They are good scientists applying different legitimate methods to genuinely ambiguous data and arriving at different conclusions, as scientists do. The question of who is right is not a question that can be settled in this room, or in any room, by argument alone. It can only be settled by K2-18b, by the planet continuing its 33-day orbit, by the star continuing to shine, by the James Webb Space Telescope, or something more powerful, collecting more light during more transits and building the statistical weight that either solidifies the signal or reveals it to be something the data was never quite robust enough to support. Both outcomes are possible, neither is certain. And that uncertainty, uncomfortable as it is not a failure of the science. It is the science operating exactly as it should when confronted with a question this hard, at the edge of what instruments this powerful can currently resolve. The scientific community's skepticism about the K2-18b detection is not arbitrary caution. It is not the reflexive conservatism of a field resistant to bold ideas. It is the accumulated wisdom of a discipline that has been here before, that has stood at what appeared to be the threshold of the most important discovery in human history, and watched the evidence dissolve under sustained scrutiny. More than once. The first time left the deepest mark. On the 7th of August, 1996, President Bill Clinton walked to a podium in the Rose Garden at the White House and addressed the world. A team of NASA scientists, he said, had found compelling evidence that might point to the possibility of ancient primitive life on Mars. He called it one of the most stunning insights into our universe that science had ever uncovered, if confirmed. He used those words, if confirmed. But the nuance disappeared almost immediately, overwhelmed by what the world wanted the announcement to mean. The rock at the center of the announcement was a meteorite. A piece of Mars blasted into space by an asteroid impact billions of years ago, drifted through the solar system for millions of years, fell through Earth's atmosphere, and landed in the Allen Hills region of Antarctica in 1984. It was recovered by a field team, catalogued and stored. Years later, a group led by David McKay at NASA's Johnson Space Center examined it in detail and found what they believed were multiple lines of converging evidence for ancient biological activity. The evidence seemed remarkable. Microscopic structures within the rock, elongated forms, smaller than any known bacterium, but structurally suggestive of fossilized organisms. Chemical compounds called polycyclic aromatic hydrocarbons, which can form when organic molecules break down, found concentrated in regions of the meteorite. Carbonate mineral globules that on Earth are sometimes associated with biological processes, and magnetic crystals of a mineral called magnetite that bore a striking resemblance to the structures produced by certain bacteria on Earth, structures those bacteria use for navigation, growing the crystals internally with a precision that, the McKay team argued, could not easily be explained by inorganic chemistry alone. Taken together, the team argued, these features were consistent with ancient Martian microbial life. Not proof, consistent with. The distinction was there in the paper. It did not survive contact with the press conference. What followed was years of painstaking analysis by dozens of research groups around the world, each examining a different piece of the evidence and asking whether it could be explained without biology. The microfossil structures turned out to be far smaller than any known living cell, small enough that serious physical constraints existed on whether anything with the complexity required for metabolism and reproduction could fit inside them. Similar structures, it emerged, could be produced through purely inorganic processes, involving the precipitation of minerals from solution under certain chemical conditions. The polycyclic aromatic hydrocarbons were found throughout the meteorite, including in regions that had clearly been exposed to Antarctic ice and the terrestrial chemistry it carries. The contamination question was real and could not be cleanly dismissed. The carbonate globules could be reproduced by high-temperature chemical reactions involving no biology whatsoever. The magnetite crystals remained the most debated piece of evidence, and in some corners of the field, they still are. There are researchers who argue, carefully and in peer-reviewed literature, that the magnetite chain structures retain biological signatures that have not been fully accounted for by abiotic models. But the overall case did not survive as a convincing ensemble. Each individual line of evidence acquired an abiotic explanation under sufficient pressure, and without the ensemble, the biological interpretation lost its foundation. The episode did not end with a dramatic single moment of retraction. It ended slowly, over years, through the grinding accumulation of alternative explanations that one by one replaced what had seemed like biological necessities with geological possibilities. It ended not with a definitive refutation, but with a gradual draining of confidence until the weight of evidence no longer supported the claim and the field moved on. What it left behind was a changed culture. Astrobiology, the discipline that studies the potential for life beyond Earth, had always been careful. After 1996, it became institutionally cautious in a way that shaped how every subsequent claim of this kind would be received. Multiple independent lines of evidence, alternative abiotic explanations systematically excluded before biological conclusions are drawn. Extraordinary evidence for extraordinary claims. The phrases became mantras. The standards became higher because the consequences of being wrong had been so publicly demonstrated. Then came 2020 and Venus. A team led by Jane Greaves at Cardiff University used the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile to observe the atmosphere of Venus at radio wavelengths. What they reported in a paper published in September of that year was the detection of phosphine, a molecule consisting of one phosphorus atom bonded to 3 hydrogen atoms, in the cloud decks of Venus at concentrations of roughly 20 parts per billion. Phosphine is a molecule with a very limited set of natural production pathways. On Earth, it is produced in 2 contexts: industrial chemical synthesis and anaerobic biological processes. Bacteria living in oxygen-free environments such as swamps, marshes, and the intestinal systems of animals, releasing phosphine as a metabolic byproduct. No known atmospheric or geological process in a planetary environment should generate phosphine at detectable concentrations, which meant that if it was genuinely present in Venus's atmosphere, something was making it. And the most plausible something, in the absence of factories on Venus, was life. The response was enormous. Scientists who had spent careers studying Venus found themselves fielding calls from journalists asking whether the discovery of life on the planet next door had just been announced. Coverage was immediate, global, and largely breathless. The planetary science community convened emergency discussions. Papers appeared on preprint servers within days. For several weeks in the autumn of 2020, it genuinely seemed as though the question of life in the solar system might be resolved not by a distant exoplanet, but by our nearest neighbor. Then the reanalysis began. The spectral feature attributed to phosphine was located at a frequency of 267 GHz. At that frequency, phosphine has a known absorption line, but so does sulfur dioxide, a gas that Venus has in considerable abundance and whose absorption pattern at that frequency overlaps with phosphines. The original analysis had attempted to account for sulfur dioxide, but had done so in a way that subsequent examination found to be insufficient. The signal attributed to phosphine was almost certainly, in part or in full, sulfur dioxide. The problem was compounded by a calibration error discovered in the reduction pipeline used to process the James Clerk Maxwell telescope data. A systematic error in the way the raw observations had been converted into a usable spectrum had artificially amplified certain features, including the feature at 267 GHz. When the pipeline was corrected and the data reprocessed, the apparent phosphine concentration dropped from 20 parts per billion to approximately 1 part per billion. At that concentration, the detection was consistent with noise. Multiple independent groups working with the same data and with alternative datasets from other instruments found no convincing phosphine signal. The detection, almost certainly, had not been real. What had appeared to be an inexplicable biological signal in Venus's atmosphere turned out to be a combination of overlapping molecular features and a processing error. Two categories of problem that are difficult to detect during analysis, precisely because they produce results that look like genuine signals. The institutional reflex that had developed after 1996 sharpened further. Spectral overlaps, calibration pipelines. The question of whether you are finding what is in the data or what is in the model. These are now the first questions asked of any detection of this kind, and they are the right questions. Set K2-18b against this history, and you will understand why the initial announcement was greeted with skepticism, even by researchers who found the data genuinely interesting. The pattern was uncomfortably familiar. Extraordinary spectral claim. Immediate media translation of qualified language into definitive discovery. Swift pushback from independent researchers. Competing analyses finding different conclusions from the same data. The detecting team defending their methods. The critics questioning the assumptions behind them. The headlines moving faster than the evidence. And yet there are reasons why K2-18b is not a direct repetition of either story, and they deserve to be stated with equal care. The phosphine detection rested on a single instrument, a single spectral feature, and a molecular identification that had a direct mundane alternative in a gas already known to be abundant in Venus's atmosphere. When the calibration error was found and the sulfur dioxide contribution properly accounted for, the signal vanished. The K2-18b detection has survived two independent instruments looking through wavelength ranges with zero overlap. The calibration of MIRI is independent of the calibration of the near-infrared spectrographs. A processing error in one would not appear in the other. The molecular identification, while contested, does not have a single obvious dominant alternative that accounts for both detections simultaneously in the way sulfur dioxide accounted for the phosphine feature. The signal has been subjected to months of internal disproof attempts by the detecting team and has not collapsed. And it was predicted by a theoretical framework 4 years before either observation was made. None of that constitutes confirmation. The history makes that plain. But it does mean the K2-18b situation is not structurally identical to what came before, and treating it as if it would itself be a failure of scientific judgment. The appropriate response is neither credulous excitement nor reflexive dismissal. It is the same thing the data demands: more evidence, more rigor, more time. The history of things that were not there is also a history of science learning to ask better questions. And right now, with the instruments we have and the planet we are watching, we are asking the best questions we have ever been capable of asking. The answer is still forming. And the next chapter of this story depends not on the past, but on what the telescope collects in the months ahead. To understand what it would actually mean to confirm a biosignature, not just detect a molecule, but genuinely confirm that life is its source, you need to go back 60 years. Back to a question that a scientist named James Lovelock asked while working at NASA's Jet Propulsion Laboratory, long before any exoplanet had been discovered, long before any instrument existed to probe the atmospheres of distant worlds. Lovelock was thinking about Mars. Specifically, he was thinking about how you would know, from a distance, whether a planet was alive. Not whether it had the right temperature or the right distance from its star, but whether the chemistry of its atmosphere bore the unmistakable signature of a biosphere actively at work. He published his answer in Nature in 1965, in a paper that established the theoretical foundation of biosignature science and whose central argument has not been seriously challenged since. The argument was this: life maintains a planetary atmosphere in thermodynamic disequilibrium. What does that mean? In a world with no life, atmospheric chemistry tends toward equilibrium, toward the stable state where all the reactive gases have had time to react with each other and settle into their lowest energy configurations. Oxygen reacts with methane and produces carbon dioxide and water. Given enough time without replenishment, those reactions run to completion and the reactive gases disappear. What remains is chemically stable, quiet, dead in the way that any system at equilibrium is dead. Still, predictable, going nowhere. Life interrupts this. A biosphere continuously pumps reactive gases into the atmosphere, gases that would otherwise react away and disappear, at rates fast enough to maintain concentrations far above what equilibrium chemistry would allow. Earth's atmosphere is in this sense profoundly out of equilibrium. Oxygen should react with methane and consume both. Both are present in significant quantities because biology keeps producing them faster than chemistry can destroy them. The atmosphere is being actively maintained in an impossible chemical state by the combined metabolic output of every living thing on the planet. That active maintenance is, Lovelock argued, detectable from space. You do not need to land on a world to know it is alive. You need only to read the disequilibrium in its air. This is the intellectual foundation of every biosignature search that has happened since, and it points immediately to why detecting a single molecule is never sufficient. Every molecule that life produces on Earth also has at least one abiotic production pathway. Oxygen accumulates when ultraviolet radiation splits water molecules, releasing hydrogen to space and leaving oxygen behind. No photosynthesis required, just a water-rich planet near an active star. Methane erupts from volcanoes, seeps from the seafloor through geological processes, and forms in the atmospheres of gas giants through purely chemical means. Phosphine, as we have just seen, was confidently reported in Venus's atmosphere before the detection collapsed. And dimethyl sulfide, as the Rosetta mission demonstrated, forms in the cold chemistry of cometary ice, without a single living cell anywhere in the process. This is not a minor inconvenience for biosignature science. It is the central epistemological problem of the entire field. Any individual molecule you detect in a planetary atmosphere has an abiotic escape route. Any single detection, however specific the molecule, can in principle be explained without invoking life. The question is not whether abiotic alternatives exist. They always do. The question is whether they can explain the specific concentrations, the specific combinations, and the specific patterns observed, or whether the only coherent explanation requires an active biological source. This is what drove the field, gradually and necessarily, away from the search for single biosignature molecules and toward what researchers now call biosignature ensembles. The canonical example is oxygen and methane together. These two molecules react with each other in the presence of sunlight. The reaction proceeds steadily. Oxygen oxidizes methane, producing carbon dioxide and water. Given a few thousand years, the reaction consumes whichever of the two is less abundant. If an atmosphere contains both oxygen and methane simultaneously at significant concentrations, something must be replenishing both faster than the reaction destroys them. On Earth, photosynthesis replenishes the oxygen. Methanogens replenish the methane. The biosphere maintains both gases in the atmosphere simultaneously against the thermodynamic pressure of the reaction that would consume them. No purely geological or photochemical process is known to replenish both gases at the rates required. The coexistence of oxygen and methane in chemical disequilibrium is the strongest biosignature ensemble currently known, not because either molecule alone is uniquely biological, but because their simultaneous presence implies a biological pump that the chemistry of an inorganic world cannot sustain. Edward Schwieterman at the University of California, Riverside produced in 2018 what became a consolidating document for this way of thinking. A comprehensive review of the full landscape of remotely detectable signs of life, covering gaseous biosignatures, surface biosignatures, and temporal biosignatures, and making the case for ensemble detection as the minimum credible standard going forward. Single molecules, his review argued, could not carry the evidential weight required. Co-detections, thermodynamic arguments, and the broader pattern of atmospheric disequilibrium were what the field needed to pursue. K218b does not have a detectable oxygen signal. In a hydrogen-dominated atmosphere, free oxygen would react with the surrounding gas and disappear almost immediately. Its absence is not suspicious, it is expected. The gold standard ensemble of oxygen and methane is therefore unavailable for this planet. What the field is left with is a source strength argument. The concentration of dimethyl sulfide is so high that abiotic processes cannot easily explain it. That is a weaker form of biosignature logic than the thermodynamic disequilibrium argument, and it depends on our knowledge of abiotic production rates being complete, which, as the magma ocean discussion makes clear, it is not. Sarah Seeger at the Massachusetts Institute of Technology has been thinking about biosignature science for longer than almost anyone in the field. In 2025, she and her collaborators published a catalogue of 15 candidate biosignature gases for exoplanet atmospheres, an expansion of the target list that went well beyond the familiar handful of molecules that had dominated the field. Among the 15 were chlorofluorocarbons, synthetic chemicals produced on Earth exclusively by industrial processes, whose detection in an exoplanet atmosphere would constitute not just a biosignature, but a technosignature, evidence not merely of life, but of technological civilization. The list reflected something important about the state of the field, the recognition that biosignature science had been too narrowly constrained by what life on Earth produces, and that genuinely alien biology operating on genuinely alien chemistry might leave atmospheric fingerprints that no Earth-centric framework had yet considered. The most consequential molecule on any near-term search list for K218b specifically is methyl chloride. It is produced on Earth by vegetation and marine organisms. It has no known abiotic production pathway that would generate it at significant concentrations in the environment of a sub-Neptune exoplanet. Its spectral absorption features lie at wavelengths accessible to the James Webb Space Telescope, and critically, it shares no plausible common abiotic source with dimethyl sulfide. If methyl chloride were detected at K2-18b, alongside the existing DMS signal, the two molecules together would constitute something considerably more powerful than either detection alone, two independent biological signatures with no common, non-biological explanation. That is the closest thing to an ensemble available at this planet given its atmospheric chemistry. It is what the field needs to see. It has not yet been looked for, or rather, the data to look for it comprehensively does not yet exist. It will. Assume for a moment, clearly, as a thought experiment grounded in the scientific models, that the signal is biological. that whatever is producing dimethyl sulfide in K218b's atmosphere is alive. What is that life actually like? What does it face? What does it require? And how different would it be from anything that has ever existed on this planet? Begin with the constraints. No free oxygen. Surface pressure at the ocean interface perhaps 100 times Earth's sea level. A hydrogen atmosphere rather than an oxygen-nitrogen one. Red dwarf UV radiation arriving in pulses during flares. A 43% variation in received stellar energy over the 33-day orbit as the planet moves between its nearest and farthest points. Permanent day on one hemisphere, permanent night on the other. And between them, the terminator, where conditions are most survivable, but the winds are most violent. This is not the environment that produced complex animals with nervous systems and large brains. It is, at best, the environment that could produce microbes. Single-celled organisms running on ancient metabolic chemistry, adapted over billions of years to conditions that have no equivalent anywhere in our solar system. The most plausible metabolic template is the methanogens. We have met them already in the context of the atmospheric chemistry they would produce, but consider them now as organisms in their own right. Methanogens belong to the archaea, one of the three great domains of life on Earth, distinct from bacteria and from the eukaryotes that include every plant, animal, and fungus you have ever seen. They are among the most ancient organisms we know, their metabolic pathways tracing back to the earliest chapters of life on Earth. They consume molecular hydrogen and carbon dioxide. They produce methane and water. They do this without oxygen, and have done so since long before oxygen existed in Earth's atmosphere. They have been found at depths of several kilometers below the surface, in temperatures exceeding 100 degrees Celsius, in environments of extreme salinity, in the near vacuum of the upper stratosphere. The range of conditions under which they remain viable is genuinely extraordinary. K218b's atmosphere contains hydrogen, it contains carbon dioxide, it contains methane. A planet whose atmosphere looks like the exhaust of a methanogen-rich ocean is not a strange or exotic prediction. It is the most straightforward biological interpretation of a chemical signature that already fits. But methanogens alone do not produce dimethyl sulfide. The DMS signal requires a separate metabolic pathway, one involving sulfur chemistry rather than carbon chemistry. The most plausible producers are sulfur metabolizing anaerobes, organisms that cycle reduced sulfur compounds the way iron metabolizing bacteria cycle iron, or nitrogen metabolizing bacteria cycle nitrogen in Earth's oceans. On Earth, dimethyl sulfide from phytoplankton is an incidental byproduct of a process that evolved for something else entirely. On K218b, if biology is the source, the organism producing it might be generating dimethyl sulfide as a primary metabolic product, perhaps through a sulfur cycle in the ocean that has no direct analog in Earth's biochemistry, but that produces the same molecular output. The scale of the biology required gives you some sense of what you would be imagining. Earth's oceans produce roughly 100 million tons of dimethyl sulfide per year from a phytoplankton population numbering somewhere in the region of 25 million billion cells. K218b's atmospheric concentration, even accounting for hydrogen's slower DMS destruction rate, implies either a vastly more productive ocean per unit volume than Earth's, or production pathways far more efficient than anything terrestrial biology has evolved, or both. The numbers are not impossible, but they are large enough to suggest that life on K218b, if it exists, is not a thin biological film clinging to marginal conditions. It is an active, productive biosphere operating at a scale that would be extraordinary, even by Earth's standards. Go deeper. Below whatever surface chemistry might be driving the atmospheric signal, below the photic zone where whatever light reaches the ocean drives energy harvesting reactions, there is darkness. And in the darkness, at the bottom of an ocean that may extend to depths we cannot yet estimate, heat from the planet's interior rises through the water column. A world 8.5 times Earth's mass has an enormous reservoir of internal heat, the accumulated energy of its formation and the ongoing decay of radioactive elements locked in its core. That heat has to go somewhere. On Earth, it finds its way out through volcanic activity, through hydrothermal vents on the ocean floor, through the slow release of warmth from the planet's interior into the water above. Hydrothermal vents on Earth support entire ecosystems. Tube worms several meters long, shrimp that navigate by the faint infrared glow of the vent itself. Microbial mats so dense they look like living rock. None of these organisms need sunlight. None of them depend on photosynthesis. They are powered by the chemistry of hot, mineral-rich fluid erupting from the seafloor and meeting cold, oxidized water above. The energy released when electrons move between reduced and oxidized compounds in the dark. These communities have been operating for hundreds of millions of years, completely independent of the surface biosphere, completely independent of the sun. A planet of K2-18b's mass almost certainly has vents. The internal heat is there. The geological activity that drives hydrothermal circulation is likely there. If the ocean exists, the vents probably exist. And if the vents exist, life analogous to Earth's vent communities could exist in them, independent of the atmospheric signal entirely, invisible to the James Webb Space Telescope, living in the permanent dark and the crushing pressure of a world that has never cared whether anyone was watching. Nancy Qiang, working at NASA's Goddard Institute for Space Studies, has spent years thinking about what photosynthesis looks like around stars other than our own. The question is more subtle than it first appears. Photosynthetic organisms on Earth evolved pigments that absorb the wavelengths of light most abundantly produced by the sun, reds and blues, the wavelengths that drive chlorophyll. A red dwarf like K2-18 emits most of its light not in the visible spectrum, but in the near-infrared. Organisms evolving in an ocean beneath a red dwarf sky, if they harvest light at all, would face an entirely different distribution of available wavelengths. They might evolve pigments tuned to the near-infrared, black or deep grey in appearance to our eyes, absorbing across the full visible and near-infrared spectrum, rather than reflecting the green that plants reflect on Earth. And because red dwarf light penetrates water more deeply than solar visible light, the zone where light-driven chemistry is possible would extend further into the water column. The entire upper ocean, not just the top few meters, might be available to photosynthetic analog life. This is the picture that the High-Sean hypothesis implies if you follow it seriously. Not life clinging to the margins of a barely habitable world. Life that has had 2 billion years to develop in a vast, pressurized, chemically rich ocean under the patient light of a star that will burn for 10 trillion years. Life that has saturated its ocean with the same molecule that fills the air above every beach on Earth. Life that, 10,000 times more productively than anything in our oceans, has been exhaling its chemistry into the sky. And something 124 light-years away, built by a species of curious and anxious primates that have existed for less than 300,000 years, has just detected the smell of it. Whether it is real or not is a question that requires more than imagination to answer. It requires more data. And that is exactly what is coming. There is a building on the west side of Cambridge where 2 research groups work within walking distance of each other. They share seminar rooms. They attend the same departmental talks. They exist within the same small community of people who have dedicated their professional lives to understanding how planets form and what they are made of. One group believes K2-18b may be a world with a hydrogen ocean and a potentially active biology. The other believes it is almost certainly a world with a magma ocean and a chemistry that mimics life without containing any. They are not enemies, they are colleagues, and they think each other is wrong about the most consequential scientific question of the century. This is, to be clear, exactly how science is supposed to work. The disagreement is not a dysfunction of the process. It is the process running at full intensity, applied to a question that matters more than almost any other. What makes it worth examining as a human story, rather than simply as a scientific one, is what it reveals about the gap between how science actually happens and how the outside world perceives it. Niku Madhusudan came to exoplanet science from theoretical physics. The shift was gradual. a growing fascination with the new class of observational data that the Kepler mission was producing, and the realization that the theoretical frameworks needed to interpret what the data was showing were still being built. His strength was in modeling, building mathematical representations of atmospheric chemistry and asking what observational signatures different models would produce. By the mid-2010s, he had become one of the leading figures in exoplanet atmospheric retrieval, a field that barely existed when he began his career. The High-Cian World paper in 2021 was, by any honest assessment, a bold move. The claim that sub-Neptune worlds with hydrogen atmospheres could be not merely habitable, but among the most promising targets for biosignature searches, was not universally accepted. The conventional wisdom had long favored rocky worlds in the habitable zones of sun-like stars as the primary targets, worlds more like Earth, around stars more like the Sun, arguing that a class of planet dismissed by much of the community as too large, too exotic, and too poorly understood should be prioritized for life detection was the kind of claim that invites skepticism. It attracted plenty. When the 2023 JWST data came in and matched what the 2021 paper had predicted, Madhusudan later described the experience as something surreal. A mathematical construct, a set of equations and model outputs that existed only on paper and in a simulation, had materialized in an observation. The telescope had found what the theory had said would be there. He used the word surreal deliberately. A scientist of his disposition does not use words like that for ordinary confirmations. Something unusual had happened to him. And then the April 2025 MIRI result arrived. The second instrument, the independent wavelength range, the same signal. He described it as a shock to the system. He said it takes a while to recover from the enormity of it. And then, in the weeks that followed the announcement, he was precise and careful in every interview, every press statement, every public communication. Potential biosignature, possible indicators. He did not say life detected. He understood, with the clarity of someone who has lived inside scientific controversy, what those words mean and what the consequences of using them carelessly would be. The media did not make that distinction. The headlines were immediate and almost uniform. Life found on alien planet. Scientists detect signs of life. The ocean world that smells of biology. Researchers who had not yet seen the full data set were contacted by journalists asking for their reaction to the confirmation of extraterrestrial life. Not the potential indication of a biosignature at 3 sigma confidence, but the confirmation of life. Several senior scientists responded publicly and critically, some comparing the announcement to the phosphine episode and arguing that the field could not sustain another cycle of headline-driven excitement followed by retraction. One exoplanet scientist at the Max Planck Institute for Astronomy, Laura Creedberg, said she had seen this movie before. She was not dismissing the data. She was identifying the pattern, the structural tendency of this type of announcement to outrun the evidence it is based on, and the cost that tendency imposes on the credibility of the field. Madhusudan pushed back on the characterization in interviews. His team's language had been scrupulously qualified throughout. The paper itself had used every appropriate hedge. The translation of potential biosignature into life found was not something he had control over, and it was not something he had encouraged. The alternative, saying nothing, sitting on a result of this potential magnitude until every conceivable objection had been pre-answered, was not obviously the right choice either. At some point, science has to communicate what it has found, and the responsibility for how that communication is received and amplified cannot rest entirely with the scientists whose names are on the paper. He had a point. The gap between precise scientific language and public understanding is not new, and it is not a failure that originates with the researchers. It is a structural feature of how science moves through a media ecosystem that rewards certainty over qualification and discovery over uncertainty. That gap has claimed the reputations of careful scientists before, and it will claim them again. The K2-18b announcement was not exceptional in this regard. It was a demonstration of a recurring problem that the field has not yet solved. On the other side of the Cambridge debate, Oliver Shortall was doing what geochemists do. starting with the rock. Shortall's approach to K218b was not to ask what life would produce and then look for it. It was to ask what a planet of this mass, this density, this bulk composition would produce geologically, and whether that geological production was sufficient to explain what JWST observed without invoking any biology at all. When his models returned an atmospheric fingerprint, methane, carbon dioxide, low ammonia, that was uncomfortably close to what the James Webb Space Telescope had actually detected. The implication was not that Madhusudan was wrong. The implication was that the data did not distinguish between the two scenarios, that two completely different physical realities could produce the same spectral output. Shortall's position, stated carefully, was not that K218b is a magma world. It was that the evidence is consistent with a magma world. The same evidence is consistent with a Hycean world. The current data cannot tell them apart. And in a field where the extraordinary interpretation is life on another planet, the standard you are expected to meet before drawing that conclusion is higher than consistency. You need to rule out the ordinary interpretation first. There is an asymmetry in this debate that the magma ocean proponents acknowledge, and the Hycean hypothesis proponents emphasize, and it is the asymmetry of prediction versus explanation. Madhusudan's theoretical framework specified the detection before the detection existed. The prediction was published in 2021. The JWST observations were made in 2023 and 2025. The magma ocean models, however rigorous, were developed substantially in response to those observations, as alternative explanations for data that already existed. In the philosophy of science, this asymmetry carries weight. A theory that makes a correct prediction before the fact is, all else being equal, stronger than a theory that explains the same data after the fact. Post hoc explanation is easier. A model with enough free parameters can always be tuned to fit existing data. A model that specifies in advance what you will find in a dataset that has not yet been collected, with an instrument that does not yet exist and is then vindicated by that dataset. That is a different kind of achievement. This does not make the Hycean hypothesis correct. Correct predictions from incorrect theories are not impossible. Ptolemaic astronomy made correct predictions about planetary positions while being fundamentally wrong about the structure of the solar system. The predictive success of the 2021 paper is real evidence, but it is not decisive evidence. What it is a reason to take the biological interpretation seriously, rather than dismissing it on grounds of simplicity alone. The most revealing thing Madhusudan said about the entire process was not about the data, and it was not about the controversy. It was about the months before the announcement. He said that his team spent that time not trying to confirm the signal, but trying to destroy it, testing every calibration assumption they had made, modeling every alternative molecule whose spectral features might produce the observed pattern, looking for every pathway by which the signal could be a systematic error, an instrumental artifact, a coincidence of overlapping features that had nothing to do with dimethyl sulfide in an alien atmosphere. They were not trying to prove themselves right. They were trying to prove themselves wrong, and after months of this, the signal was still there. That is what good science looks like from the inside. Not the triumphant press conference, not the headline, not the cautious or incautious language used in the announcement. The long, unglamorous, methodical work of attempting to falsify your own result before anyone else can do it for you. The strange and uncomfortable experience of running out of ways to make the signal disappear. Whether the signal is real remains genuinely open. The debate is unresolved, the data is insufficient, and the answer will not come from argument. It will come from K2-18b itself, from the photons that continue to arrive at our telescopes, carrying the chemical record of a world 124 light-years away. Both camps have submitted proposals for additional telescope time. Both will analyze whatever comes next, with the same rigor they have brought to everything so far. The building in Cambridge will still be there when the results arrive. The two groups will still be within walking distance of each other, and one of them will have been right. The question of what K2-18b's atmosphere actually contains is not going to be answered by the data that currently exists. It is going to be answered by data that has not yet been collected, by observations that may already be in the queue, or may be planned, or may still be awaiting approval from committees that allocate time on instruments that the entire world's astronomers are competing to use. The James Webb Space Telescope is the most oversubscribed scientific instrument in human history. Every year, research groups from dozens of countries submit proposals for observing time. The proposals are reviewed by a committee and assessed on scientific merit. The number of hours requested across all proposals vastly exceeds the number of hours available. Most proposals are rejected. The ones that are approved represent the collective judgment of the field about which questions are most worth pursuing with the most powerful tool available. K218b has already received substantial JWST time, 2 full transit observations, each requiring several hours of continuous uninterrupted data collection, each competing for allocation against hundreds of other compelling proposals. The Cambridge team has submitted requests for additional transit observations. Whether and when those are approved and what the resulting data shows will be the next major chapter in this story. Here is what additional JWST transits could establish. The current signal sits at 3 sigma. Each additional observation adds photons to the dataset. More photons means a higher signal-to-noise ratio, which means more precise measurement of which wavelengths are being absorbed and by how much. If the signal is real, if there genuinely is a sulfur-containing organic molecule in K2-18b's atmosphere at the concentration suggested by the existing data, then each new transit observation should strengthen it. The confidence level should rise. 2 to 3 additional observations, combined with the existing data in a joint analysis, could potentially push from 3 sigma to 5 sigma if the underlying signal is genuine. If the signal weakens as more data arrives, if the apparent detection at 3 sigma reflects statistical noise that additional photons dilute rather than amplify, then it will fade. Not dramatically, not with a single decisive moment of refutation, but gradually as the curve that points toward a detection flattens and the argument for a significant molecular identification loses its foundation. The data will arbitrate. It always does. There is a second observational requirement that goes beyond simply accumulating more transits at the existing wavelengths. Distinguishing between dimethyl sulfide and dimethyl disulfide, the 2 molecules whose overlapping spectral features at current JWST resolution prevent a clean identification, requires observations at wavelengths beyond 12 micrometers. In that part of the mid-infrared spectrum, the absorption features of the 2 molecules diverge sufficiently to be individually resolved. MIRI, the James Webb Space Telescope's mid-infrared instrument, has sensitivity that extends toward the longer wavelengths where this distinction becomes possible, though the signal-to-noise challenges at those wavelengths are substantial. Whether dedicated observations in that range can be accomplished with the telescope's current capabilities, and at what cost in observing time, is an active question. What is clear is that no reanalysis of existing data will resolve the ambiguity. New observations at new wavelengths are the only path forward on the molecular identification question. And then there is what comes after JWST. In the Atacama Desert of Chile, at an elevation of over 3,000 meters on a mountain called Cerro Armazones, construction is underway on what will be the largest optical and infrared telescope ever built. The extremely large telescope, being constructed by the European Southern Observatory, will have a primary mirror 39 meters in diameter, composed of 798 individual hexagonal segments, each about 1.5 meters across, together forming a light-collecting surface that exceeds anything currently in operation or under construction by a factor of several. Its total light-collecting area is roughly 6 times that of the James Webb Space Telescope. First light is expected around 2030. What that additional light-gathering power means for spectroscopy is not simply a proportional improvement in sensitivity. The spectrographs the extremely large telescope will carry are designed to resolve individual molecular absorption lines with a precision that JWST cannot approach. Where JWST blurs together the overlapping features of closely related molecules, the extremely large telescope will be able to separate them. The DMS versus DMDS ambiguity that currently cannot be resolved, the identification problem that sits at the heart of the K2-18b controversy, is the kind of problem the extremely large telescope's instruments were built to address. That said, the extremely large telescope is a ground-based observatory. It is optimized in its core design for rocky planets around nearby stars rather than sub-Neptunes at K2-18b's distance. The telescope will have its most transformative impact not on K2-18b specifically, but on the planetary systems closest to us. The TRAPPIST-1 system, a compact arrangement of 7 rocky planets around a red dwarf star about 40 light-years away, several of which sit within the habitable zone, and Proxima Centauri b, a potentially rocky world orbiting the nearest star to our own Sun at just over 4 light-years. These planets are targets that JWST can observe in transit, but not characterize in sufficient detail to search credibly for biosignature ensembles. The extremely large telescope, with its resolving power and sensitivity, may be able to take that next step. The TRAPPIST-1 planets represent what K2-18b is not. Small, rocky, Earth-scale worlds with densities consistent with silicate and iron compositions, lacking the thick hydrogen envelopes that make sub-Neptunes simultaneously easier to observe and harder to interpret. If any of the TRAPPIST-1 habitable zone planets, and researchers have focused particular attention on TRAPPIST-1e, which receives a stellar flux closest to what Earth receives from the Sun, retain stable atmospheres and carry biosignature gases in those atmospheres, the extremely large telescope has a plausible path toward detecting them. That would be a different kind of discovery from K2-18b entirely. A rocky world, in many ways more Earth-like, closer to home, potentially showing signs of life in an environment we understand far better than a hydrogen ocean world we have no nearby template for. Further out on the horizon, far enough that it belongs to the generation of scientists currently in school rather than the generation currently writing papers, sits the Habitable Worlds Observatory. This is NASA's planned successor to the James Webb Space Telescope for exoplanet science. The concept, as developed in NASA's long-range planning, is a large space telescope optimized for a single defining purpose: the direct imaging of Earth analog planets around Sun-like stars, not transiting sub-Neptunes, not planets detected by the dimming of a small red dwarf. Planets like Earth, orbiting stars like the Sun, at orbital distances like Earth's, imaged directly, their light separated from the overwhelming glare of their parent star by an internal coronagraph or an external star shade floating in formation, some tens of thousands of kilometers away. Launch is currently planned for sometime in the 1940s, a timeline that reflects the engineering complexity involved and the scale of the investment required. The Habitable Worlds Observatory is asking a different question from the one JWST is asking at K2-18b. K2-18b is a sub-Neptune, hydrogen-dominated, tidally locked, orbiting a red dwarf. The Habitable Worlds Observatory is designed for worlds more like our own, around stars more like our own, where the biosignature ensembles we understand best, oxygen and methane in thermodynamic disequilibrium, the full suite of gases a biosphere maintains in a planet's air, could be searched for comprehensively for the first time. Kevin Hand, an astrobiologist at NASA's Jet Propulsion Laboratory, was among the scientists who helped shape the agency's astrobiology strategy, the institutional document that defines how NASA thinks about the search for life and allocates resources within it. The strategy reflects something important about where the field is. The K2-18b result, whatever it ultimately turns out to be, sits within a larger architecture. It is not an isolated event. It is one data point in a planned, systematic, decades-long program of investigation that extends from the current capabilities of the James Webb Space Telescope through the Extremely Large Telescope and into the era of the Habitable Worlds Observatory. Each instrument addresses the questions its predecessor could not answer. Each discovery, or each careful non-detection, shapes what the next instrument is designed to find. K218b will almost certainly be resolved long before the Habitable Worlds Observatory launches. The planet that is driving the most intense astrobiological debate of the 2020s will have been settled one way or another by instruments that already exist, pointing at a world we have already identified, reading light that is already arriving. The question of whether it harbors life is not a problem for the next generation. It is a problem for this one. For the scientists currently arguing about retrieval methods in Cambridge and Oxford and Chicago. For the committees deciding how to allocate time on the most powerful telescope humanity has ever pointed at the sky. The answer is close. Whether it is close enough to be in the data that currently exists, or whether it requires 2 more transit observations, or 5, or a different instrument entirely, that is what we are waiting to find out. Close your eyes for a moment, or let them rest half open, the way they do when you are drifting between thought and sleep, and try to build a world. You are standing at the terminator, the boundary between day and night on a planet that has never known the difference between morning and afternoon, between the angle of a rising sun and the angle of a setting one. The star has never moved, not once in 2 billion years. It hangs on the horizon ahead of you, low and red and enormous, the color of cooling iron, its light thick and amber rather than white, casting shadows that have always fallen in the same direction, at the same angle, since before the first complex cell existed anywhere on Earth. Behind you, the dayside blazes. The air above it, heated and expanding, rises and flows in a constant wall of hydrogen wind toward where you are standing, rushing from the permanent noon into the permanent night. The wind does not stop. It has never stopped. It is the planet's heartbeat, not a rhythm, but a constant, a roaring exchange of energy between a hemisphere baked for billions of years and a hemisphere that has never seen the star directly. Before you, the night side, black and frozen, temperatures plunging to 60 degrees below zero or colder, the air contracting and sinking and flowing back along the surface toward the day. A landscape that has never been illuminated by anything except the distant stars and whatever faint thermal glow rises from the planet itself. Where you are standing is the only place on this world where conditions sit between those 2 extremes. The terminator, the ring of perpetual twilight. And if you could breathe the air here, which you cannot, because there is no oxygen, only hydrogen and trace carbon gases, and the chemistry of a world nothing like your own, you would notice something. The smell, overwhelming, saturating, impossible to ignore. The smell of a living ocean, amplified beyond anything you have ever encountered on any beach on any coast of Earth. 10,000 times more concentrated than the air above the most productive phytoplankton bloom in the most biologically active stretch of the Southern Ocean. The combined chemical exhalation of a planet, rising from below, carried on the hydrogen wind, filling the air of this terminator strip with the unmistakable molecular signature of something alive. Look down. Beneath the hydrogen atmosphere, beneath the pressure of a sky so heavy it would crush your lungs before you could draw a breath, there is water. A global ocean with no shore, extending across the entire planet in every direction without interruption. The surface is not the blue of a summer sea. It is dark, pressurized, lit only by the faint red wavelengths that penetrate the deepest through the hydrogen canopy above. The pressure at the surface is 100 times what you would feel standing at sea level on Earth. The temperature is well above boiling by any standard your body understands, but the water remains liquid under the weight of the sky. It is not the water of a glass or a river. It is water under conditions that have no name in your language. In the upper layers of this ocean, just below the surface, something stirs. Not something you could see with the naked eye. Not something with a shape you would recognize. Single-celled organisms, if they are organisms, moving through the compressed warm water, metabolizing compounds no laboratory on Earth has studied in this combination, producing as a byproduct of their metabolic lives the molecule that is filling the air above you. They do not know you are here. They have no concept of being observed. They are simply living in the way that life lives, consuming, transforming, exhaling, reproducing, in a world that has given them 2 billion years to do exactly this. Deeper, in the crushing cold dark below the photic zone, something else may be happening. Where the ocean floor meets whatever lies beneath it, heat from the planet's interior rises through cracks in the rock, and the chemistry of hot reduced fluid meeting, cold oxidized water drives, reactions that release energy, organisms that have never needed sunlight cluster around those vents, as they cluster around the vents on the floor of every ocean on Earth, powered not by the star above, but by the planet itself. They have been there since before the surface organisms existed. They may still be there when the surface organisms are long gone. This is the Hycean world, one possible K2-18b, one face of the planet behind the signal. Now change one thing. Keep everything external the same. The red star motionless on the horizon, the hydrogen wind, the atmospheric chemistry that the James Webb Space Telescope has measured twice from 124 light-years away. Keep the signal exactly as it is, and change only what lies beneath. There is no ocean. Below the hydrogen atmosphere, where the Hycean model places water, the temperature is not the temperature of a pressurized ocean. It is the temperature of a furnace. Molten rock, glowing at thousands of degrees, churns in slow, massive convection cells that take centuries to complete a single rotation. The surface, if you can call it that, is a sea of orange and dark red, lit from within by its own heat, continuously disrupted by convection that brings material up from the deep interior and drags it back down again in an endless geological cycle. At the boundary between this magma ocean and the hydrogen atmosphere above, violent chemistry occurs continuously. Volcanic gases erupt upward, nitrogen dissolves downward into the melt, carbon reacts at high temperatures and pressures with the hydrogen above, producing methane. Sulfur compounds released from the interior interact with the chemistry of the overlying gas and generate slowly sulfur-containing organic molecules, including, in small quantities, dimethyl sulfide, not in one event, not through any biological process, but continuously, across billions of years, in a planet-wide furnace that has been running since the world formed. The chemistry of heat and sulfur and carbon and hydrogen producing, as an incidental product of purely geological processes, the same molecule that 2 independent instruments on the James Webb Space Telescope have just detected. No life, no ocean, no organisms in the dark water exhaling their chemistry into the sky. Just rock, just heat, just the ancient indifferent chemistry of a planet that has never needed biology to produce what looks, from 124 light-years away, like the smell of the sea. These 2 worlds are the same world. Right now, at this moment, one of them exists. The other is a model. They have the same atmospheric composition as far as every instrument we have ever pointed at K2-18b can determine. The same spectral fingerprint at every wavelength the James Webb Space Telescope has examined. The same carbon-bearing molecules in the same proportions. The same trace signal in the same part of the mid-infrared spectrum. You cannot tell them apart from where we sit. That is the thing worth sitting with quietly before we go further. We have built the most sophisticated scientific instrument our civilization has produced. We have positioned it at a gravitational equilibrium 1 million miles from Earth and cooled it to within a few degrees of absolute zero. We have pointed it at a planet 124 light-years away and detected specific molecules in its atmosphere at concentrations of parts per billion, from light that left that star before the First World War. We have done all of this, and we still cannot answer the most basic question about that world. Is anything alive there? The universe is not making this easy for us. It is not arranging the evidence so that the answer is obvious. It is presenting a signal that is genuinely ambiguous, a world that presents 2 completely different physical realities depending on which set of models you trust, a debate that cannot be resolved by cleverness or argument or any amount of reanalysis of the data that currently exists. It will be resolved by more light, more photons, more transits, more time. Perhaps that is appropriate. The question of whether life exists beyond Earth is not the kind of question that should yield easily. It should require everything we have. The planet turns on its 33-day rhythm, indifferent to the question it has started. The hydrogen wind blows from the blazing day to the frozen night, carrying its chemistry around the terminator and back again. Whatever is producing the signal, ocean or magma, biology or geology, the exhalation of life or the exhaust of heat, continues without knowing it is being observed, continues without knowing we exist. That is the present state of the most consequential scientific debate of our time. In 1950, the physicist Enrico Fermi was eating lunch at Los Alamos National Laboratory with several colleagues. The conversation had turned to recent reports of UFO sightings and then to the broader question of extraterrestrial intelligence. Fermi thought about it for a moment and asked a question that has not been satisfactorily answered since. Where is everyone? The galaxy contains something in the range of 400 billion stars. A significant fraction of them host planets. A significant fraction of those planets orbit within habitable zones. The universe is 13.8 billion years old. Even if life arises rarely, even if intelligent life is rarer still, even if the development of technology capable of interstellar communication or travel requires extraordinary conditions, the sheer scale of the numbers seems to demand that something, somewhere, should by now have made itself known. The galaxy should be, on the basis of probability alone, teeming with evidence of other minds. And yet we have heard nothing, found nothing, detected no signal, no artifact, no modification of any star or planet that could not be explained by natural processes. This is the Fermi paradox. It is not really a paradox in the formal logical sense. It does not assert a direct contradiction. It is an observation about the gap between what the numbers seem to predict and what the observations actually show. And in the 70-odd years since Fermi asked the question at that lunch table, no answer has emerged that satisfies everyone. Now consider what a confirmed detection of life at K218b would do to it. If biology arose independently on K218b, on one of the first habitable zone exoplanets we examined closely, with the first instrument capable of performing the relevant measurement, it would tell us something profound about the prior probability of life in the universe. It would tell us that life is not a singular accident on one lucky planet around one ordinary star. It would tell us that life is something the universe does, a process, not an exception. Something that emerges perhaps inevitably wherever the physical conditions allow, at a frequency high enough that the first serious attempt to find it at a distant world succeeded. And if life is common, if microbial biology emerges routinely across the galaxy wherever temperature, chemistry, and energy sources align, then the Fermi paradox does not become less troubling. It becomes considerably more so. Here is why. The observation that the galaxy appears silent despite its apparent habitability has several possible explanations. One is that life is extraordinarily rare, that the conditions required are so specific that we are genuinely alone, or nearly so, and the silence is simply the silence of an empty cosmos. That explanation is comfortable, in a way. It makes the silence unsurprising. But if life is common, and yet the galaxy is still silent, the silence requires a different explanation. Something happens to life, or to the intelligent civilizations that occasionally emerge from it, that prevents them from persisting long enough, or spreading far enough to make themselves detectable. This hypothetical barrier is called the Great Filter. The question that has haunted every serious treatment of the Fermi paradox is whether the Great Filter lies behind us or ahead. If it lies behind us, if the improbable steps were in the origin of life itself, or in the development of complex cells, or in the emergence of multicellular organisms, or in the evolution of technological intelligence, then we are extraordinarily lucky survivors of a filter that stops almost everything else. The silence around us is the silence of a cosmos, where most life never got started. We got through. If the great filter lies ahead, if life arises commonly, if intelligence arises somewhat less commonly, but still at meaningful frequency, and yet civilizations reliably fail or destroy themselves, or simply stop before achieving the kind of longevity that leaves a detectable mark on the galaxy, then confirmation of life at K218b is a warning, not a comfort. A warning that the silence has a cause we have not yet encountered, and that we may be approaching it. A confirmed independent origin of life at K218b would not answer this question, but it would transform it from a philosophical curiosity into the most urgently practical scientific and existential question our species has ever faced. The history of astronomy is, in one reading, a history of successive displacements from the center. Copernicus placed the sun where Earth had been. Subsequent centuries revealed that the sun itself is an unremarkable star in the outer reaches of a galaxy containing hundreds of billions more. Edwin Hubble demonstrated that the Milky Way is one of what turned out to be roughly 2 trillion galaxies in the observable universe. Each step moved humanity further from any privileged position in the cosmos, and each step was resisted before it was accepted, because the demotion it implied was genuinely difficult to absorb. Confirmed extraterrestrial life would be the next step in that displacement. The last remaining claim to cosmic uniqueness, that whatever else is true about our position in the universe, Earth is the only world where chemistry became biology, where matter organized itself into something that could wonder about its own existence, would be gone. Life would be something the cosmos makes. Earth would be one of the places where it happened to make it. How would people receive that? The honest answer is that we do not know, because nothing like it has ever happened before. Survey research in recent years from groups at institutions including the University of Arizona and the SETI Institute has found that when people are asked directly, most say they expect to respond to a confirmed detection of extraterrestrial life with curiosity and awe rather than crisis. But surveys ask people to predict their emotional responses to events they have never experienced. And the history of such predictions is not encouraging as a guide to how the actual experience lands. What is clearer is that the major intellectual and religious traditions of the world have been thinking about this possibility seriously. The Vatican's Pontifical Academy of Sciences has addressed the question of extraterrestrial life multiple times, with positions ranging from open curiosity to the view that a universe that produces life is an expression of the same creative principle that the theological tradition has always described, that finding life elsewhere would expand, not threaten, the framework. Buddhist and Hindu cosmological frameworks, which have never centered human beings as uniquely spiritually significant in the way that some Western traditions have less to reconcile. Many indigenous cosmological traditions have always understood the cosmos as populated with living presences of various kinds. The philosophical diversity of how humanity already thinks about this question is itself a resource, a range of frameworks available for absorbing an answer that, if it comes, will come for everyone simultaneously and will leave no tradition unchanged. Michael Wong, an astrobiologist at Carnegie Science, looked at the state of the field in the spring of 2025 and said something that was at once simple and precisely right. What a lucky time to be alive. He was not being casual. He was identifying something specific and historically unprecedented. We are the first generation of human beings to have the instruments, the planetary targets, and the methodology to ask whether life exists beyond Earth with real data, not with philosophy, not with theology, not with the long accumulated longing of every person who ever lay in the grass on a summer night and looked up and wondered, with a spectrograph, with photons, with numbers on a screen in a laboratory in Cambridge. Whether those numbers are telling us what we hope they are telling us remains genuinely open, but we are the first to be close enough to ask. And that fact, whatever the answer turns out to be, is one that no previous generation of human beings has been able to say. There are two futures for K218b. Only one of them is real, and we do not yet know which one it is. Consider the first. The additional transit observations are completed. The data is processed, the retrieval models are run, and the statistical analysis returns a number that is smaller than the one before it. The curve that had been climbing flattens. The dimethyl sulfide feature, examined with more photons and more wavelengths, turns out to be a spectral ambiguity that accumulates in limited datasets and dissolves when the sample size grows. Jake Taylor's flatline was the more accurate description of what the atmosphere contains. The magma ocean models, refined with new thermal emission data, match the observations with no remaining residual that requires biology to explain. The signal was real in the sense that the instruments measured something. It was not real in the sense that it required life to produce. This outcome is not failure. It is not the collapse of a field or the discrediting of the scientists who found the signal and reported it honestly. It is the scientific process working as designed, a detection at 3 sigma that the community subjected to rigorous scrutiny, demanded independent verification for, and ultimately could not confirm. The threshold held. The higher standard prevented a premature claim from hardening into accepted fact before the evidence warranted it. The methods developed in the controversy, Jake Taylor's unbiased retrieval, the magma atmosphere chemistry models from Oliver Shortall's group, the joint analysis frameworks that combine multi-instrument datasets, are permanent contributions to the field regardless of what K218b turns out to be. And the search does not pause, not for a moment. There are dozens of sub-Neptunes in habitable zones identified by existing surveys and awaiting deep atmospheric characterization. There are rocky worlds in the habitable zones of nearby red dwarfs that the extremely large telescope will be able to examine with a resolution the James Webb Space Telescope cannot achieve. There is the TRAPPIST-1 system, 7 rocky planets in tight orbit around a red dwarf, 40 light-years away, at least 3 of them potentially habitable, waiting for instruments powerful enough to read their air. Every false alarm in the history of astrobiology has refined the methods used in the next attempt. K218b, if the signal fades, will have done the same. The search would be sharper for it, more honest about what the data actually shows, better equipped for the target that comes next. A resolved false alarm at K2-18b is not the end of the story. It is the end of a chapter. Now consider the second future. The transit observations continue. The confidence climbs. 4 sigma. The team waits. Another window, another analysis, the careful accumulation of photons from a planet that transits every 33 days. The curve crosses 5. Independent research groups at other institutions run their own retrievals on the same raw data and return the same answer. The thermal emission data rules out a magma ocean surface. The temperature profile of the atmosphere is inconsistent with the thousands of degrees interface that Shortall's models require. New observations extend into wavelengths that separate dimethyl sulfide from dimethyl disulfide, and the identification resolves. It is the former. And then, the detail that closes the abiotic escape routes more completely than anything else could. Methyl chloride is detected alongside it. 2 molecules with no shared abiotic production pathway in a sub-Neptune environment. Both present, both confirmed. A press conference is scheduled. The room is quiet in the way that rooms are quiet before something irreversible happens. Madhusudan stands at a podium and says, with the same precision he has used throughout, words that he has been careful not to say for 3 years. Not potential indicators, not possible biosignature. Life, microbial, on a world we will never visit. 124 light-years away in the direction of Leo, in an ocean beneath a sky of hydrogen, exhaling the same molecule that rises from every beach on Earth. The world absorbs this the way it absorbs everything, unevenly, at different speeds, through argument and reaction, and the slow grinding work of integrating a new fact into every framework it touches. Some people feel it immediately as a shift in the ground beneath them. Some need days. Some find it confirms what they always believed. Some find it challenges beliefs they did not know they held. Scientists write papers. Philosophers write arguments. Theologians write carefully. Children ask questions their parents cannot answer. And then something else happens. Something that may matter more than the announcement itself. Every star in the sky becomes a different kind of object. Not a light source, not a navigational marker, not a cultural symbol. A question. A specific, scientific, answerable question, with real instruments attached to it, and real funding pursuing it. The field reorganizes around the new prior. If life arose independently on one of the first habitable zone exoplanets we examined, then the galaxy is populated, and the question shifts from whether life exists elsewhere to where it does not. The Fermi paradox, which had been a philosophical curiosity for 75 years, becomes the most urgent scientific problem humanity has ever faced. If life is common and civilizations still do not persist, the silence of the cosmos is not a comfort. It is a data point, and we are a young civilization with nuclear weapons and a warming atmosphere, and the data point applies to us. That is the weight of what a confirmation would carry. Not just wonder, and a question that presses. But set that aside for now, because there is something more immediate, more personal, that sits at the center of this story, regardless of which future K218b delivers. We are the first, not the first to wonder whether life exists beyond Earth. That question is as old as the capacity to ask questions, and every human culture that has ever existed has carried some version of it. Not the first to think carefully about the conditions life requires, or to build theories about other worlds, or to dream of what might be out there in the dark between the stars. People have been doing all of that for thousands of years. What we are the first to do is to ask the question with instruments capable of detecting the answer. With a telescope positioned at a gravitational equilibrium 1 million miles from Earth, cooled to within a few degrees of absolute zero, reading the chemistry of an alien sky from light that crossed 124 light-years to reach it. With methods precise enough that the presence of a specific molecule at concentrations of parts per billion in the atmosphere of a world we will never visit is a thing we can measure and argue about and begin to understand. Every philosopher who proposed that other worlds might exist was working without the means to look. Every astronomer who first turned a telescope on the sky was centuries away from the instruments needed to ask this question in any form that could receive a factual answer. Every scientist who built the foundations of spectroscopy, of planetary science, of atmospheric chemistry, of astrobiology, they were building toward this moment, without most of them knowing it, without any of them being able to reach it in their own lifetimes. We are the generation that reached it. The answer is not yet confirmed. It may be weeks away. It may be months. It may require the extremely large telescope and the decade after this one. It may be that the signal at K2-18b resolves into noise and the next serious candidate is a world we have not yet identified. But the infrastructure exists, the techniques exist, the targets exist. The question that has been carried by every human generation that has ever lived is, for the first time, close enough to an empirical answer that the people working on it can taste the proximity. The planet continues its 33-day orbit. It does not know we are watching. It does not know the argument it has started, the methods it has provoked, the conversations it has forced between researchers who work in the same building and see the same data and arrive at opposite conclusions. It continues regardless. The red star burns as it has burned for 2.5 billion years, dimly, patiently, pouring its amber light onto a tidally locked world that has never experienced a sunrise or a sunset, that will never experience one, that will continue its locked and patient orbit for billions of years after we are gone, regardless of what we find. The light from that star is arriving at our telescopes right now. It left 124 years ago, carrying within it the chemical diary of an atmosphere we are still learning to read. It has been traveling since before anyone alive today was born, since before the grandparents of anyone alive today were born, crossing the dark between the stars at the only speed the universe allows, patient, indifferent, carrying its message whether we were ready to receive it or not. We were not ready, for most of that journey. We became ready recently, very recently, in the scale of things. The stars overhead tonight are the same stars that watched the first human beings look up and ask whether something was looking back. Unchanged, indifferent to the question, burning with the same ancient physics, in the same ancient dark, without any knowledge of the creatures beneath them who built, over thousands of years of accumulated effort, an instrument sophisticated enough to begin to find out. 124 light-years away, toward Leo, a dim, red star is burning, and around it, a world is turning, locked to its star, breathing out, smelling of the sea.